Hello there and welcome to Simply About Earth, the place where curiosity takes its shoes off, settles in and begins to wonder about everything that came before us. Tonight, we're slipping back, not just a few centuries or millennia, not even a million years. We're going billions deep into a time that has no photographs, no fossils you'd recognize, and no comforting sense of modern geography. A time when the continents looked nothing like the ones we know, when the air was unfamiliar, and life, if you could call it that, was mostly invisible, busy making some of the most important decisions in the history of the planet. Before we dive into this incredible journey, let me know in the comments where you're watching from. I love hearing from viewers all around the world, and it helps me understand how far these stories about deep time are reaching. Tonight, we're visiting the Proterozoic Eon. Maybe you've never heard that word before. It's okay. Most people haven't. It doesn't show up in casual conversation. It doesn't headline museum banners or pop into school curriculums as often as dinosaurs or mass extinctions. But the Proterozoic is vast, unimaginably so. It spans from about 2.5 billion years ago to just 541 million years ago. Over half of Earth's history is tucked inside that stretch. That means if you lined up everything that's ever happened from trilobites to tyrannosaurs to Twitter, the Proterozoic is the long, quiet prelude. But it wasn't dull, not remotely. This was the age when Earth's surface was reshaped again and again, when continents collided and cracked apart, when the sky began to fill with something entirely new and slightly toxic to many early residents: oxygen. When microscopic organisms invented photosynthesis without asking anyone's permission, when cells teamed up, merged, and accidentally created the foundations for everything that would come later, including us. The rocks from this time don't tell their stories easily. They whisper, if they speak at all, but buried in those layers are traces of the first great ice ages, the first complex cells, the first experiments in cooperation, the first hints that life wasn't content staying small and simple. If the Archean was Earth's chaotic childhood, the Proterozoic was its slow, sprawling adolescence, awkward, dramatic, and filled with irreversible changes. So, if you're ready to drift, let's go back to a time when the sun was dimmer, the moon was closer, and a day wasn't 24 hours yet. A time before animals, before plants, before the world had a name for what it meant to be alive. Back when Earth was still figuring itself out. No rush. We've got billions of years ahead of us, and it all begins with a world just waking up. The Earth at the start of the Proterozoic was already more than a billion years old. It had been battered by meteorites, smothered in volcanic eruptions, and cloaked in a hazy atmosphere filled with gases that would be lethal to us now. There were oceans. Yes, but they weren't the clear blue pools we imagine today. They were murky, metallic, and anoxic, meaning they lacked oxygen entirely. In these early waters, iron drifted freely, dissolved in abundance, giving the seas a reddish tint in some places. The land, what little there was of it, was bare rock. No trees, no soil, no buzzing of insects or rustle of leaves, just silence, wind, and the slow work of chemistry. This was not a dead world, but it was quiet. The kind of quiet that settles in when life is small and slow and very, very busy with important things. Single-celled organisms were already thriving. They had been for a long time. Tiny ancient forms of bacteria and archaea had figured out how to survive in extreme environments, boiling vents, salty pools, places with no light and plenty of sulfur. They weren't glamorous, but they were incredibly good at what they did. They broke down minerals, absorbed and released gases, built structures too small for any eye to see, and in doing so they began to reshape the planet from the inside out. The continents were starting to take shape, though they didn't resemble anything familiar. Early supercontinents, names like Columbia or Nuna, if you go looking, were assembling. They drifted slowly across the mantle, guided by convection currents that churned in the Earth's molten interior. Plate tectonics was already in play, but it hadn't yet carved out the dramatic mountain ranges or deep ocean trenches that mark today's map. Instead, land masses were low, flat, and volcanic. Erosion hadn't yet built thick layers of sediment, and without plants to anchor the soil, any loose material was at the mercy of wind and rain. Rivers existed, but they behaved differently. Lakes formed in impact craters or in cracks where the crust had pulled apart. Everything was more raw, more direct, the elements at work without the interference of large, complicated ecosystems. Sunlight reached the planet, of course, but it wasn't quite as bright as it is now. The sun, still in its early stages of maturity, shone about 85% as strongly as it does today. That lower energy output meant the Earth had to hold on to heat more carefully, which it did in part thanks to greenhouse gases like methane and carbon dioxide. The atmosphere was thick with them. There was no ozone layer, so ultraviolet radiation poured in from space, making the surface a dangerous place for anything fragile. Life stayed underwater, mostly tucked beneath layers of ocean that acted as a protective shield. Deep water was safer, quieter, and more stable. Meanwhile, the crust beneath it all continued to shift and evolve. Early versions of continents had begun forming long before, but during the Proterozoic, the process of craton building picked up speed. Cratons are the ancient cores of continents, the geological elders of the land beneath your feet. Once they form, they tend to stick around, stable, thick, and resistant to deformation. They're the backbone of today's continents. Much of North America, for example, sits on a craton that first solidified during this time. Africa, too. Australia. Pieces of these land masses have survived billions of years of collision, rifting, erosion, and volcanic upheaval. They are survivors from an era when the surface of the planet was still figuring out how to hold itself together. One of the more subtle transformations happening during this period was in the planet's mantle. Radioactive decay was a major source of heat, and over time that heat drove cycles of melting and remelting, helping to create new rock types. Granite became more common, so did certain minerals that would later be important for life. Phosphorus, for instance, or molybdenum. These elements didn't know they would someday help run enzymes or build DNA, but their availability would quietly shape the possibilities of biology for the rest of time. And in the oceans, something new was stirring. Among the countless microbes, a particular group had begun to master a difficult and risky form of energy production. They were bacteria, but different from the sulfur eaters and methanogens that came before. They had learned how to use light, not just any light, but the full, unfiltered sunlight that pierced the shallow oceans, and with that light, they cracked open water molecules to release energy. As a byproduct, they gave off something unusual: oxygen. This would turn out to be one of the most important and disruptive events in Earth's history. But for now, it was just beginning. Tiny bubbles of oxygen, invisible and irrelevant, drifting through waters that had no idea what was coming. The world was still sleeping in a way, but someone had just cracked open a window, and soon the atmosphere would never be the same. The oceans of the early Proterozoic were unlike anything we would recognize. There was water, yes, and lots of it. Vast, sprawling basins covered much of the planet just as they do now, but the chemistry, the color, the texture of those ancient seas belonged to another world entirely. These were anoxic oceans, meaning there was no free oxygen dissolved in them, and that fact changed everything. Without oxygen, many of the biological processes we take for granted simply couldn't happen. Respiration, as most modern organisms know it, didn't exist. Instead, microbial life relied on other pathways, ones that could seem alien to us today. They metabolized sulfur compounds, produced methane, used iron and nitrogen in ways that seem more like chemistry experiments than life strategies. It worked, but it was slow, and the returns were limited. These were ecosystems built on fermentation, not fire. The color of the water itself may have ranged from dull green to murky red, depending on location. Iron was everywhere, floating freely in its dissolved form. In modern oceans, iron is scarce, quickly oxidized and precipitated out. But back then, with no oxygen to trigger that reaction, the oceans held iron in abundance. It drifted through the water column until eventually something would cause it to precipitate out. Often, when oxygen-producing microbes released their waste, that triggered a chemical reaction, and the iron would rust, falling out of solution to the ocean floor in massive sheets. This is how we got banded iron formations, layered rock deposits that are still mined today. They formed over hundreds of millions of years in rhythmic cycles of iron-rich and iron-poor sediment. Each band tells a story about chemical balances, about fluctuations in microbial activity, about a planet in chemical transition. They are among the best geological records we have of the Proterozoic oceans, and they only form in these kinds of oxygen-poor, iron-rich environments. Life thrived in these early seas, but you wouldn't have seen it. There were no fish, no seaweed, no corals or crabs or even plankton in the modern sense. Life was almost entirely microbial, existing in layers and films and mats. If you had the technology to observe closely, you might find stromatolites, layered structures built by colonies of cyanobacteria and other microbes. They grew slowly, layer by layer, trapping sediment and building mineralized domes over time. Some grew in shallow tidal flats, others deeper down. Many were covered by sediment and preserved as fossils, though modern examples still survive in a few isolated spots on Earth. These microbial mats were more than just clusters of cells. They were ecosystems, complex, layered communities where different types of bacteria occupied different zones, depending on how much light and which chemicals were available. The top layers performed photosynthesis while the lower layers consumed the byproducts and recycled nutrients. It was a vertically organized, self-sustaining world packed into just a few centimeters of mud and slime. Deeper in the ocean, away from the light, other microbes dominated. Archaea and bacteria adapted to low-energy environments, often living near hydrothermal vents or buried within sediments. Their metabolisms were slow, their lives measured in days or weeks rather than hours, but they were persistent, and they played a key role in regulating the ocean's chemistry. Without large animals to stir the sediment, the seafloor was a still, dark place where chemical gradients could develop over vast stretches of time. Methane was a major player in this world. Certain microbes called methanogens produced it as a metabolic byproduct, releasing it into the water and atmosphere. Methane is a potent greenhouse gas, and its abundance likely helped keep the planet warm despite the sun's reduced output. For much of the Proterozoic, the atmosphere may have been a mix of nitrogen, carbon dioxide, water vapor, and methane, with only the faintest traces of oxygen. The interaction between these gases and the ocean's chemistry was delicate. Small changes in microbial activity could lead to major shifts in atmospheric composition. And once photosynthesis began producing oxygen in earnest, the chemistry tipped. Not quickly, not dramatically, but slowly. Over millions of years, the balance started to change. Oxygen reacted with the dissolved iron, with methane, with sulfur compounds. It disappeared as fast as it was made, but the microbes kept going. They didn't need to understand the consequences of what they were doing. They just kept performing the same chemical trick, splitting water, capturing light, releasing oxygen, and the oceans began to rust. This process didn't happen evenly across the globe. Shallow waters near microbial mats saw the most immediate change, while the deep ocean remained anoxic for much longer. Scientists refer to this layered condition as a stratified ocean, oxygen-rich at the surface and anoxic below. Over time, as oxygen levels increased and penetrated deeper, the ocean's chemistry evolved. Sulfur began to play a bigger role. Hydrogen sulfide, a gas produced by certain microbes in low oxygen conditions, accumulated in mid-depth waters. This created regions that were both anoxic and sulfidic, lethal to most modern life, but perfect for the microbes of the time. Some researchers call these oceanic conditions. They were toxic, yes, but stable, and they may have persisted on and off for hundreds of millions of years. It's a reminder that habitability is a moving target. What would kill us today was normal back then, and what we call extreme environments now were the norm for much of the planet's early history. The oceans before oxygen were quiet, chemically complex, and biologically rich in their own subtle way. They supported life, but life that played by very different rules. They were places of slow transformations, of invisible revolutions in metabolism and energy use, and they were the stage on which one of the greatest disruptions in Earth's history was about to unfold, because eventually those oxygen bubbles started to add up. It didn't start with a bang. It didn't even start with a splash. There was no sudden moment where the oceans flipped color or where the sky shifted overnight. The great rusting of the seas, as it's sometimes called, was a drawn-out transformation, slow, silent, and utterly world-changing. Oxygen, when it first appeared in measurable quantities, was more of a pollutant than a resource. The single-celled microbes that had been producing it, primarily cyanobacteria, didn't do it for our benefit. They were just trying to survive, to make energy more efficiently by capturing sunlight and splitting water molecules. It was a clever trick, biologically speaking, but chemically it had enormous consequences. Free oxygen is highly reactive. It doesn't just hang around, it wants to bind with things, especially metals like iron. And there was a lot of iron. Dissolved iron floated freely in the ancient oceans, giving the water a greenish or brownish cast depending on conditions. It had nowhere else to go since oxygen hadn't been around to take it out of circulation. But now, as tiny amounts of oxygen began to accumulate, the rules changed. Every molecule of oxygen that bumped into an ion triggered a reaction. Iron oxidized, it rusted. Not in the flaky red-brown way we see on old cars or garden tools, but in a microscopic, suspended way. The oxidized iron formed insoluble particles and began to fall out of the water column. Over time, those particles settled on the seafloor, building layer after layer of iron-rich sediment. These layers hardened into rock, and what we're left with today is banded iron formations, sheets of stone that alternate between iron-heavy layers and lighter, silica-rich ones. They're found on nearly every continent, thick sequences in Australia, Canada, South Africa, Brazil. They vary in thickness, in color, in mineral content, but they all point to the same thing, a long, ongoing chemical shift in the planet's oceans. The process wasn't smooth. It came in waves, periods where oxygen production increased, followed by times when it slowed. Sometimes the oxygen made it far enough to oxidize huge swaths of the ocean. Sometimes it stayed local, trapped near the microbial mats that produced it. The Earth was learning to breathe in fits and starts. This rusting phase likely lasted hundreds of millions of years. And it wasn't just a pretty mineral phenomenon. It was the beginning of a cascade. As more and more iron got pulled out of solution, the oceans became chemically depleted in ways that pushed other changes. Oxygen began to persist in surface waters. It started to leak into the atmosphere. Methane, once a dominant greenhouse gas, reacted with it and broke down but had a cooling effect, which would matter later. But even before that, the presence of free oxygen created entirely new pressures on life. For many anaerobic organisms, oxygen was toxic. It damaged their enzymes, interfered with their metabolism. For a time, large portions of the biosphere were poisoned by the very gas we now depend on. Entire lineages may have gone extinct, erased quietly by chemistry they couldn't adapt to. Others found ways to cope. Some microbes evolved enzymes to detoxify oxygen's harmful byproducts. Others moved deeper into the sediment, away from the light and the new chemical threat. Evolution didn't pause. It adjusted. The rocks preserve some of this story. In places where the banded iron formations end, where the layers abruptly disappear, we see hints that the oceans had run out of iron to rust. Oxygen had done its job. It had scoured the seas clean of free iron, leaving behind a different world, one where oxygen could finally begin to accumulate in the atmosphere in earnest. This event, the Great Oxygenation Event, didn't happen overnight. It was more like a multi-act play with quiet intermissions and occasional reversals, but it marked a turning point. The Earth's chemistry had been altered in a fundamental way. The oceans had gone from iron-rich and anoxic to something else, something that could support different forms of life, and eventually something that could sustain complexity. The color of the ocean changed too. Without iron to give it a rusty tint, the water likely became clearer in many places. As oxygen levels increased, even slightly, different microbial communities rose to prominence. Light could penetrate deeper, new ecological layers formed. From a distance, the planet still looked much the same. Blue oceans, grey continents, white clouds, but internally, things had shifted. The rusting of the seas wasn't just about minerals, it was about momentum. The change had begun that couldn't easily be undone. Oxygen had found a foothold, and it wasn't going away. The next steps wouldn't be smooth. The oxygen spike led to cooling, methane dropped, greenhouse warming declined, and Earth teetered on the edge of its first major deep freeze. But for the microbes in the shallows, things were going according to plan. They had made a world in their image whether anyone noticed or not, and somewhere in a quiet pool, the oxygen kept bubbling up. It's easy to overlook the importance of something so small. Cyanobacteria are microscopic, just tiny loops and chains of cells floating or clinging to rocks, often in places you wouldn't think to look. But what they lack in size, they make up for in impact. In the early Proterozoic, they were among the most consequential organisms the planet had ever seen. They didn't roar, stamp, or fly. They didn't build anything with bones, but they changed the chemistry of the Earth, and they did it with sunlight and patience. Cyanobacteria weren't the first living things, far from it. Life had been around for over 1 billion years by the time they rose to prominence, but they were different in a fundamental way. They had figured out oxygenic photosynthesis. This was a biochemical trick that allowed them to take in carbon dioxide and water, absorb energy from sunlight and use it to build sugars. In the process, they split water molecules and released oxygen as a byproduct. No one asked them to do it. They didn't coordinate or plan. This wasn't innovation in the conscious sense. It was the result of mutations, trial and error, chemical opportunism. But it worked, and once it worked, it spread. Oxygenic photosynthesis was far more efficient than the earlier versions of photosynthesis used by other bacteria, which relied on sulfur or hydrogen. That efficiency gave cyanobacteria an edge. They could grow faster, colonize new environments, outcompete their neighbors. Slowly, their populations expanded. Mats of cyanobacteria formed in tidal flats, on submerged rocks, around the edges of shallow lagoons. Some floated freely, drifting in the upper layers of the sea, capturing sunlight wherever it reached. These mats weren't just loose communities, they were layered systems, often with other bacteria living beneath the cyanobacteria, feeding on their waste products or using different wavelengths of light. Together they formed stable, resilient ecosystems. They created gradients of light, oxygen, and nutrients. They cycled elements and built structures. Over time, they even helped to form stromatolites, those dome-shaped, layered rocks that still turn up in fossil beds today. Stromatolites were more than geological curiosities. They were the physical record of microbial activity preserved over thousands of years. They built up grain by grain as microbial mats trapped sediments, secreted minerals, and protected themselves with slimy coatings. The result was a laminated tower of biology and geology, a slow monument to persistence. In the early Proterozoic, stromatolites were everywhere. They dotted the shallow seas, spreading across coastlines and reef-like margins. They were one of the dominant ecosystems on the planet. Not in size, but in coverage. These structures represent some of the oldest visible life on Earth, and many of them were built by cyanobacteria or similar organisms. But their real legacy wasn't in the rocks. It was in the air. The oxygen released by these microbes didn't make a big difference at first. It was absorbed by iron in the oceans, by volcanic gases, by organic matter. For millions of years, the atmosphere remained mostly unchanged. But as the Great Rusting progressed, the sinks for oxygen began to fill up. Iron levels dropped, reactive gases were consumed, and eventually the oxygen had nowhere to go but up. Cyanobacteria didn't stop. They continued releasing oxygen, oblivious to the long-term consequences. They weren't trying to reshape the world, they were just running their metabolic programs, but they became agents of transformation. The oxygen they released began to build up in the atmosphere, altering the balance of gases and triggering a cascade of environmental changes. One of the early effects was on climate. Methane, a major greenhouse gas at the time, is highly sensitive to oxygen. When oxygen levels increased, methane levels fell. This reduced the greenhouse effect, contributing to global cooling. It's likely that the first major ice ages in Earth's history were linked, at least in part, to the rise of cyanobacteria and the atmospheric shifts they set in motion. Their impact on life was even more dramatic. For many anaerobic organisms, oxygen was lethal. It interfered with their cellular machinery, disrupted their energy production, damaged their DNA. Entire ecosystems were upended. Microbial communities had to retreat to deeper sediments, more isolated environments, places where oxygen couldn't reach. Others adapted. The oxygen crisis, as it's sometimes called, forced evolution down new paths. Some microbes developed antioxidant defenses, some began to use oxygen themselves, evolving aerobic respiration, a much more efficient way to extract energy from food. This opened the door to greater complexity, faster metabolisms, new cellular structures. Cyanobacteria weren't the end goal. They were a catalyst. They created conditions that allowed eukaryotic cells to emerge, and eventually multicellular life. Their presence reshaped the biosphere, the atmosphere, the chemistry of the oceans. They didn't know they were writing a new chapter in life's story, but they were. Modern descendants of these organisms still exist. They're found in ponds, on wet rocks, in hot springs and deserts. They're the green scum on a stagnant pool, the slippery coating on a river stone. They're not glamorous, but they're ancient, resilient, and still running the same biochemical playbook that changed the world billions of years ago. Every breath of air you take contains oxygen that exists because of them, not just because of what they're doing now, but because of what they did then, in the Proterozoic, when they covered the Earth in thin blue-green layers and quietly began one of the most important transformations in planetary history. For something so fundamental to modern life, oxygen had a very awkward debut. It wasn't invited, it wasn't expected, and for many of Earth's earliest organisms, it was a massive inconvenience. What we now call the Great Oxygenation Event, or GOE for short, was not a party. It was, in many ways, a slow-motion catastrophe for the microbial world. It began innocently enough. Cyanobacteria, as established, had been releasing oxygen into their surroundings through photosynthesis. At first, that oxygen didn't last long. It was absorbed by iron in the oceans, by gases from volcanic activity, by decaying organic matter. It was like pouring water onto a dry sponge. For millions of years, the oxygen never made it into the atmosphere in any meaningful way. It just disappeared into the chemistry of the environment. But sponges have limits. Eventually, the sinks began to fill. The iron got used up, buried as banded iron formations. Volcanic gases shifted, slowed, or got consumed. The ocean chemistry gradually tilted, and one day, though of course no one was counting days back then, oxygen started to linger. It didn't vanish, it began to accumulate in the atmosphere. This was not a sudden event. The oxygenation process likely took tens of millions of years, but in geological terms that's a fast shift, and for many anaerobic organisms that had evolved in a world without free oxygen, it was a disaster. Oxygen is a highly reactive molecule. It damages proteins, lipids, and DNA. In small amounts, it creates oxidative stress. In larger amounts, it's toxic. For microbes adapted to reducing environments, The rise of oxygen was like flooding their world with acid. Entire microbial ecosystems collapsed or were forced into marginal environments. Anaerobic bacteria retreated to deep sediments, hydrothermal vents, and other low-oxygen niches. Some lineages went extinct altogether. The biosphere didn't die, but it reorganized sharply. Those that could adapt survived, others disappeared, leaving only chemical traces in the rocks. On a planetary scale, the consequences were just beginning. Methane, which had been one of the key greenhouse gases maintaining Earth's warmth under the dim young sun, began to break down in the presence of oxygen. The atmosphere cooled, reflective ice began to form at the poles and possibly spread toward the equator. Earth may have experienced one of its first global-scale glaciations, or at least a sharp climatic downturn. This interplay between biology and climate, between microbial metabolism and planetary temperature, marked a new stage in Earth's evolution. The planet had begun to regulate itself in a way that was dynamic, interconnected, and occasionally a little brutal. The oxygen also changed atmospheric chemistry. Ozone began to form in the upper atmosphere, a molecule made of 3 oxygen atoms. Ozone is unstable near the surface, but useful higher up, where it absorbs harmful ultraviolet radiation from the sun. Before the GOE, life could only survive underwater or deep in rocks, because UV radiation at the surface was intense and unfiltered. But with ozone slowly building up, the surface began to soften, becoming less hostile to life's next steps. This created a feedback loop. More oxygen meant more ozone meant less UV radiation. Less radiation meant safer conditions for shallow water and eventually surface life. The GOE, though rough in its early phases, laid the groundwork for later biological expansion. But it wasn't all upward and onward. After the initial rise in oxygen levels, the atmosphere likely entered a period of instability. Oxygen levels rose and fell in pulses. There may have been feedback crashes where new biological innovations or geological events caused oxygen to drop again. The early Proterozoic atmosphere was a patchwork of gases, not a stable mix, and for organisms trying to survive in it, adaptability was everything. The term oxygenation sounds pleasant, almost clinical, but to many of Earth's earliest life forms, it was more like a slow poisoning, followed by a long recovery. Even for the survivors, it meant change. New metabolic strategies had to evolve. Some microbes began using oxygen in their energy cycles, developing aerobic respiration. This process was far more efficient than anaerobic pathways, allowing cells to extract much more energy from the same amount of food. And that efficiency opened doors. Larger cells became possible, more energy meant more complex internal structures, repair mechanisms improved. Eventually, one lineage of microbes developed internal compartments, including one that specialized in oxygen processing, the mitochondrion, but that comes later. For now, oxygen was still finding its place. It lingered in the atmosphere, slowly rising. It seeped into soils and minerals. It created new types of chemical weathering, reshaping the surface of continents. The red beds, oxidized sedimentary rocks found worldwide, are part of this legacy. They formed when iron in soils reacted with atmospheric oxygen, staining entire rock layers with that familiar rusty hue. It's strange to think of oxygen as an environmental toxin, but in the early Proterozoic, that's exactly what it was. It caused extinctions, reshaped ecosystems, altered the climate, and left a lasting geological signature. It also made the modern biosphere possible. But at the time, none of that was obvious. The planet had turned a corner. Life was still small, still microscopic, but its waste product had changed the atmosphere, the oceans, and the direction of evolution itself, all without a plan. Just cells floating in the shallows, soaking up sunlight and doing what they'd always done, breathe in carbon dioxide, breathe out oxygen, and let the rest of the world figure out what to do about it. The sky above the early Proterozoic Earth would not have looked like ours, at least not consistently. Depending on when you stood, If you could stand on that raw rocky surface, and depending on the gases hanging in the atmosphere at the time, you might see a sky tinted with hues that feel more like science fiction than geology. Not the familiar pale blue with its tidy horizon line, but something murkier, heavier, and shifting. The skies were in the middle of a transformation, and like everything else in the Proterozoic, it was happening in slow motion. Back before oxygen took hold, the Earth's atmosphere was rich in gases like methane, carbon dioxide, water vapor, nitrogen, and hydrogen. Volcanic emissions poured out sulfur compounds. Ultraviolet radiation from the sun came in mostly unfiltered. Without an ozone layer, there was nothing to block the incoming UV, and without oxygen in large quantities, there was no mechanism to create ozone in the first place. Methane, in particular, played a starring role. It's a greenhouse gas, yes, but it also has interesting effects on light. When present in high concentrations, methane can create a haze, an atmospheric soup of organic particles known as tholins. On early Earth, it's possible that such a haze filled the sky, scattering light and tinting the air with oranges or browns. It might have resembled something between a perpetual sunrise and a stormy dusk, depending on the thickness of the haze and the angle of the sun. Then oxygen arrived. As free oxygen began to accumulate, it reacted with methane. The breakdown of methane reduced its presence in the atmosphere, and with it, the hazy orange filter started to lift. The sky cleared, the scattering of sunlight shifted, and for the first time, the atmosphere began to behave in a way more familiar to us. It's hard to pin down exactly when the sky turned blue, at least in the consistent way we experience it now. The change wasn't binary. There was no sudden click from brown to blue. Instead, it was gradual, a slow erosion of the old haze and a building up of the new clarity. Sunlight filtered through an evolving mix of gases. The blue we associate with a well-oxygenated atmosphere emerged over time as oxygen levels rose. Methane declined, and ozone began to form in the upper layers. Ozone, for its part, is created when ultraviolet light splits oxygen molecules, O2, into individual oxygen atoms, which then recombine with other O2 molecules to form ozone, O3. Once this process got going, it introduced a vital layer of protection high above the surface, something that had never existed before. The ozone layer absorbed much of the UV radiation that had previously bombarded the surface unchecked. For the first time, shallow water and eventually even land began to seem a little less hostile, not safe exactly, but survivable. This protective layer also helped stabilize the atmosphere, at least in terms of radiation exposure. With less UV hitting the surface, organic molecules could persist longer. Mutations still happened, of course. Evolution didn't stop, but the environment became less immediately destructive. That change, in turn, opened more ecological space for microbes to explore. The visual impact of all this would have been noticeable if there were eyes to see it, and eventually there would be. The clarity of the atmosphere would have changed the way light behaved on the surface. Shadows grew more defined, colors became sharper, sunsets began to take on the fiery gradients we still see today. Not that there were viewers yet. No animals to blink against the glare or marvel at the horizon, just microbial mats quietly going about their chemical routines, while above them the sky changed character. This shift also affected temperature. With less methane and more carbon dioxide, the greenhouse effect was altered. Methane traps heat more efficiently than CO2, so its decline likely contributed to a drop in global temperatures. In the long run, this cooling trend helped pave the way for the first major glaciations, ice ages that would wrap the planet in frost, possibly from pole to equator. But before the snow came, the light changed. The rocks from this period don't capture the sky directly. They can't tell us what shade of blue hovered over the first land masses, or how sunlight played on the surface of an early stromatolite reef. But they can hint. Red beds, those iron-rich sediment layers, form when iron in soils and sediments react with atmospheric oxygen. Their presence tells us that oxygen had made its way into the air in meaningful quantities enough to alter the way rocks weathered, enough to leave a permanent color signature in the geological record. It's strange to think that sky color is tied to chemistry. We take it for granted. We glance up and expect blue during the day, red at sunset, black scattered with stars at night. But that entire palette is a product of atmospheric composition, of gas mixtures and radiation angles, of molecules reacting to light. In the Proterozoic, the sky was still deciding what it wanted to be, and slowly it settled into a look we would later come to call normal. Meanwhile, down below, life continued. The microbial world didn't care much about the aesthetics of the upper atmosphere, but it benefited from the changes all the same. Oxygen wasn't done yet. It was still climbing, and with it came pressure, adaptation, and eventually a whole new kind of cell. If you're enjoying this journey through deep time so far, hit that like button. Your support really helps Simply About Earth continue bringing these stories from the ancient world to life, and it lets me know that you want to hear more about the incredible transformations that shaped our planet long before anything resembling us ever existed. They didn't have blueprints. They didn't plan, no scaffolding, no tools, no architects in the usual sense, and yet, these ancient microbial mats were the first communities to leave lasting marks on the landscape. Long before coral reefs or termite mounds or human cities, mats of bacteria were building something surprisingly sophisticated, a cooperative living structure. Layer upon layer, cell by cell, they spread across shallow seafloors, tidal flats, lagoon edges, and coastal platforms. Wherever sunlight could reach, and water didn't churn too violently, these mats found a foothold. They were thin at first, just sheets of photosynthetic bacteria clinging to surfaces, held together by mucus-like secretions. But over time, the mats grew more complex. They developed vertical structures, stacked communities, gradients of light, oxygen, nutrients, and waste. It was zoning by chemistry. The top layers were dominated by cyanobacteria. They were the ones doing the heavy lifting, capturing sunlight, splitting water, producing oxygen, and synthesizing sugars. Just beneath them were other microbes, anaerobes that used the cyanobacteria's waste products, hydrogen sulfide users, nitrogen fixers, fermenters. Everything had its niche. The deeper you went, the less oxygen there was, and in those low oxygen or anoxic zones, the microbial metabolism shifted. Instead of generating oxygen, these organisms broke things down. They recycled, they decomposed, they turned organic material back into usable forms for the layers above. It wasn't a hierarchy, it was a loop. Some of these mats trapped sediments, tiny grains of sand and silt carried in by tides or currents. Others precipitated minerals out of the water using their metabolic byproducts. Over time, these processes built up layered structures, flat at first, later more domed or columnar. These became stromatolites. Some formed isolated clumps, others spread for kilometers, covering entire coastal shelves in microbial patchwork. Stromatolites are still found in a few places today: Shark Bay in Australia, some hypersaline lagoons, a few alkaline lakes. Modern examples grow slowly, often in harsh conditions where grazing animals or modern seaweeds don't interfere. There are echoes of a time when these structures were everywhere. In the Proterozoic, stromatolites were among the dominant surface features of the shallow ocean, not because they were tall or fast-growing, but because there was so little competition. Nothing else built permanent, mineralized structures on this scale. Nothing else engineered its environment in such a visible, layered way. These weren't just biological communities, they were geobiological machines. Each layer of a microbial mat performed specific functions, and the entire structure regulated its internal chemistry. Oxygen was produced in one place and consumed in another. Sulfide was generated in one layer and used in the next. Carbon cycled through photosynthesis, respiration, and fermentation. It was dense with activity, even if it looked like little more than a greenish slime from the outside. The mats altered their surroundings. They influence sediment stability, trapping grains and building microenvironments. They changed the composition of nearby waters, altering pH and redox conditions. They were, in a way, tiny cities, systems with neighborhoods, specializations, waste management, energy generation, and defense. There were no predators, not yet. But competition still existed. Different strains of bacteria competed for space, for light, for access to nutrients. Some mats produced antimicrobial compounds to keep out invaders, others grew faster or adapted to slightly deeper waters. Evolution didn't wait for eyes or limbs to get clever. The architecture wasn't made of stone or bone, but it was durable. Stromatolites preserve well, especially in carbonate-rich environments. The layers lithified over time, turning into rock. Some preserved microfossils, tiny filaments and spheres that hint at the cells that built them. Others preserved only textures, but either way the record is there. These structures tell us more than just who lived where. They offer clues about the chemistry of the oceans, the levels of oxygen, the intensity of light. They tell us which microbes were thriving and which environments supported complexity. They also mark time. Layers build slowly, so counting them, measuring them, analyzing their composition gives geologists a way to trace environmental changes across millions of years. There's also something quietly profound about how long these mats held their place. For most of the Proterozoic, microbial mats were the dominant ecological form, not a side story, not a niche. They were the headline for over 1 billion years. No other life form came close to displacing them. The slow, coordinated, layered life strategy worked, and so it persisted. Eventually things would change. New cells would arrive, grazers would evolve, the stability of the mats would be disrupted. But that was still far off. For now, in the middle of the Proterozoic, they were the primary engineers of the biosphere, shaping coastlines, regulating chemistry, building quiet cities one layer at a time. For most of Earth's history, life didn't have eyes. It didn't have mouths or spines or bones. There were no wings cutting through the air or fins slicing through water. There was no movement, not in the way we think of it. Nothing hunted, nothing fled. There was no seeing, no reacting to light beyond the level of molecules and membranes. And yet, life thrived. The Proterozoic Eon was a microbial world. Everything was small. Nearly everything was single-celled. The diversity was enormous, but almost all of it unfolded at the microscopic scale, not because larger life was impossible, but because there had been no need yet for it. No arms race, no chase between predator and prey, no survival pressure that required speed, complexity, or central coordination. Microbes ruled through chemistry, not behavior. They shaped their environment by existing, by breathing, by excreting. Every cell was a little factory running ancient metabolic scripts: absorb, convert, release. There were no faces to read, no limbs to wave, but there was communication. Chemical signals passed between cells, gradients that told microbes where to move, when to grow, whether to divide. They moved when needed. Some had flagella, whip-like tails that let them swim toward nutrients or away from danger. Others drifted with currents, passive passengers in water columns. Some clung to surfaces, some sank and waited. Life didn't need to be fast. It needed to be efficient. Lack of eyes didn't mean a lack of light sensitivity. Many microbes responded to light, especially those involved in photosynthesis. Cyanobacteria positioned themselves in water columns to catch just the right wavelengths. Some even adjusted their depth as light changed with the time of day or water turbidity. They had no vision, but they had photoreceptors, molecular systems that triggered changes in behavior when light hit them. The microbial biosphere was structured by gradients: light at the top, darkness below, oxygen in some places, anoxia in others, temperature, pH, salinity, all varied in layers and pockets. Microbes specialized. Some thrived only in the narrow band where two conditions overlapped, others endured extremes: heat, salt, acidity, pressure. The variety was immense, even without visible features. This was not a static world. Genetic change was constant, bacteria reproduce quickly, and each division carries the possibility of mutation. Over millions of years, this allowed for extraordinary diversification. Horizontal gene transfer, where microbes shared genes directly, sped things up even more. Traits like photosynthesis, nitrogen fixation, or resistance to toxins could hop between lineages. Evolution didn't wait for complexity. It found every available shortcut. The fossil record from this time is limited. Most microbes didn't leave behind hard parts. Their bodies decayed quickly, but they did leave chemical signatures, biosignatures. Certain molecules like hopanes or steranese point to the presence of specific kinds of bacteria. Stable isotope ratios suggest who was doing photosynthesis, who was digesting sulfur, who was fixing nitrogen. The rocks remember, even when the cells themselves are long gone. Sometimes preserved mats or sediments trap impressions of ancient microbial life, tiny filaments, cell clusters, mineralized remains, not photographs, but traces. Just enough to piece together a picture of a world teeming with life, even if none of it had faces. The ecosystem was self-sustaining. Primary producers, photosynthesizers, created energy-rich molecules. Consumers broke them down. Decomposers finished the job. It was a full food web, just stripped of any physical drama. No jaws, no chase, just molecules moving through layers of mud and water, slowly but endlessly. Time moved differently here. Without complex nervous systems, there was no awareness, no memory, no planning. Cells responded to their environment in real time through chemistry, a signal, a change, a reaction. That was the rhythm of life. And for all its simplicity, this system was stable. It lasted for over 1 billion years. No collapse, no extinction events as we think of them. There were shifts, sure. New metabolisms arose, oxygen levels changed, climate fluctuated, but the microbial biosphere adjusted. It absorbed shock. It filled every niche and recycled every molecule. It's tempting to think of this time as a prelude, a slow build-up to the real action. But that's not how evolution works. There is no finish line. The microbial world wasn't waiting for eyes or legs or intelligence. It was complete in its own way, finely tuned, successful on its own terms. Many of the lineages that dominated then are still here now. Some have barely changed. Their descendants live in our guts, in our soil, in our oceans. Others were ancestral to entirely new forms of life. Eukaryotes, multicellular organisms, animals. But at this point in the Proterozoic, that future hadn't happened yet. This was their time, a world shaped by cells too small to see, building empires of chemistry, surviving without sight, without sound, without anything we'd recognize as awareness. And still, they were the most powerful force on the planet. The reign of the microbes wasn't just long, it was foundational. And in one corner of this invisible world, something new had begun to stir, something with a nucleus. They didn't appear with a flash. No dramatic split, no ancient flag planted in the mud. Eukaryotes, the cells that would one day build all plants, animals, fungi, and everything complex in between, arrived quietly. Like so many things in the Proterozoic, their appearance wasn't sudden. It was gradual, messy, and wrapped in uncertainty. But when they did emerge, they marked a major departure from everything that had come before. A eukaryotic cell is more than just a membrane and some cytoplasm. It's compartmentalized, organized, internally specialized. It has a nucleus where its DNA is kept safe behind a second membrane. It has organelles, tiny structures with specific roles, mitochondria to make energy, endoplasmic reticulum to process proteins, a cytoskeleton to maintain shape and guide movement. It's not a bag of chemicals. It's a system with traffic patterns, logistics, storage, and oversight. None of that existed in earlier life. Prokaryotes, bacteria, and archaea are simple by comparison. efficient but stripped down. Their DNA floats free in the cell. Reactions happen more or less wherever conditions are right. That simplicity works. It's worked for billions of years. But eukaryotes took a different route. They opted for internal complexity. How that happened is still debated. The leading explanation is symbiosis, a kind of cellular merger. At some point, an archaeal host cell took in a bacterial partner, not as food, but as a collaborator. Maybe the bacterium started living inside the host, protected from the outside world. Maybe it offered something in return, like the ability to use oxygen efficiently for energy. Whatever the exact circumstances, the partnership worked. The bacterium stayed. It lost its independence, shed unnecessary genes, and became an organelle. Over time, it evolved into what we now call a mitochondrion. This wasn't the first time life merged, but it was one of the most consequential. Suddenly, the cell had a dedicated energy center, one that could churn out far more ATP, the molecule cells use for fuel, than any previous metabolism allowed. That extra energy made everything else possible. It allowed for larger genomes. It supported the cost of running internal compartments. It gave rise to the potential for cell specialization, for regulation, for scaffolding, for shape. It was, in evolutionary terms, a major upgrade, not required, but powerful. The earliest eukaryotes were still single-celled. They weren't multicellular yet. They didn't have brains or limbs or recognizable features, but they had potential, and they began to diversify. Some became ancestors of algae, others branched toward what would become fungi or animals. They took different paths, tried new forms. Many of those experiments didn't last. Evolution is full of false starts, but some lineages persisted, and over time the eukaryotic tree filled out. What marks this period is not abundance, but innovation. Eukaryotes weren't dominating ecosystems. They were newcomers in a microbial world still ruled by bacteria and archaea, but they were doing things differently. Some developed flexible membranes and the ability to engulf other cells. This opened the door to predation, a new kind of ecological interaction. Life wasn't just absorbing molecules from the environment anymore. It was starting to feed on other life. This was a subtle but enormous shift. It created selective pressure for defense, for mobility, for detection. Eukaryotes didn't need eyes yet, but they needed awareness, chemical sensing, environmental responsiveness, the ability to move toward or away from stimuli. Life was beginning to think spatially. They also started forming more elaborate relationships with each other. Some became hosts to other symbionts. Certain groups eventually took in photosynthetic bacteria, likely cyanobacteria, and those guests became chloroplasts, the organelles that power modern plant cells. Again, the pattern was the same: cooperation, integration, specialization. The fossil record is sparse, but there are clues. Microfossils with more complex structures, larger with signs of internal compartments, appear in Proterozoic rocks. Chemical markers like certain sterones point to eukaryotic metabolisms. It's not always definitive, but the hints align with molecular data, which suggests that eukaryotes had already split into major groups by the middle Proterozoic. In a way, these cells were worlds unto themselves. They carried within them layers of history, bacterial ancestry, archaeal roots, symbiotic mergers. Their complexity was inherited, not designed. Nothing about it was inevitable, and yet it opened doors that couldn't be closed again. With more energy, more control, and more genetic material, they were positioned to do something new, build multicellular bodies. That wouldn't happen right away. There were still hundreds of millions of years left in the Proterozoic, but the blueprint was now in place. The cell wasn't just a building block anymore. It was a system ready to cooperate, ready to become something larger. For now, eukaryotes remained small, scattered, and outnumbered, but their presence marked a turning point. Complexity had entered the game, and the next moves would take even longer to unfold. When cells began absorbing other cells instead of digesting them, something strange happened. What was supposed to be lunch turned into partnership. Symbiosis in the simplest sense means living together, and in the early Proterozoic, it wasn't always voluntary, but it was effective. One of the most important outcomes of this unplanned intimacy was the mitochondrion, the structure that still powers nearly every eukaryotic cell today. The mitochondrion is often described as the powerhouse of the cell, but that phrase, repeated in textbooks and biology quizzes, barely hints at the story behind it. Mitochondria didn't start as organelles. They began as free-living bacteria, likely a type of alpha-proteobacterium capable of using oxygen to produce energy efficiently. These bacteria had a metabolism well suited for a planet in the early stages of oxygenation. But instead of continuing on independently, one of them ended up inside another cell and stayed. How that happened is still debated. Some theories propose that the host cell engulfed the bacterium through a process like phagocytosis, pulling it in as a potential food source. Others suggest a more mutual beginning, perhaps the host provided protection, and the bacterium offered useful chemical outputs. Either way, the result was not digestion but accommodation. And over time, what started as cohabitation became permanent. The bacterium transferred many of its genes to the host cell's nucleus. It lost its autonomy, its ability to live on its own. It became dependent. And so did the host. The bacterium provided a consistent internal source of adenosine triphosphate, ATP, the cell's main energy currency. In exchange, the host cell gave it raw materials, shelter, and control over its reproduction. This was not a smooth transition. It took millions of years, but gradually the merged entity stabilized, and the mitochondrion became a fixture, a cell within a cell, a biological merger, so complete that most modern eukaryotic cells cannot survive without it. Mitochondria still carry traces of their bacterial past. They have their own DNA, separate from the cell's nucleus. They reproduce independently, dividing in a way that resembles bacterial fission. They have double membranes, one likely from their original bacterial envelope, the other from the host's engulfing process. Their ribosomes and some proteins resemble those of bacteria more than those of their host. This cellular fusion marked a turning point in evolution, not because it made eukaryotes more interesting, but because it made them more powerful. Aerobic respiration, the process used by mitochondria, produces many times more energy per molecule of glucose than anaerobic methods. That extra energy meant cells could grow larger, they could maintain complex internal structures, they could copy more DNA, produce more proteins, and perform more functions. Energy made complexity sustainable. The impact of mitochondria isn't just metabolic, it's ecological. Cells with mitochondria could exploit more environments. They could tolerate oxygen and eventually depend on it. They could form new kinds of communities, interact in new ways, build new structures. The quiet absorption of one bacterium into another opened the door to the entire tree of complex life. Some eukaryotes went further. They formed additional symbioses in lineages that would become algae and plants. Another major merger occurred. A photosynthetic cyanobacterium was engulfed and retained. This event, separate from the mitochondrial one, gave rise to the chloroplast, the organelle responsible for capturing sunlight and producing energy from light. Like mitochondria, chloroplasts have their own DNA, double membranes, and bacterial ancestry. Symbiosis, once seen as a biological footnote, is now recognized as a driver of major evolutionary transitions. It's not just a survival strategy, it's a creative force. Instead of discarding the foreign, early eukaryotes incorporated it. Instead of rejecting the other, they made it a part of themselves, and in doing so they rewrote what a cell could be. The mitochondrial origin story also challenges tidy narratives about competition. Evolution isn't only about outcompeting rivals, it's also about integration. The most successful organisms aren't always the fastest or strongest. Sometimes they're the ones that learn to live together. Even now, mitochondrial function affects every aspect of eukaryotic life, from muscle contraction to neural activity, from reproduction to aging. The energy economy of the cell runs through these ancient bacterial descendants. When mitochondria fail, systems collapse. When they're efficient, life flourishes. They are not optional accessories. They are the foundation of our biology. And yet, they're still separate in a way. Each mitochondrion carries a tiny genome, a molecular fossil of a time when it was free. It has no awareness of its past, no memory of the engulfing, but the lineage remains. Every mitochondrion in every animal, plant, and fungus is a direct descendant of that ancient bacterial partner taken in more than 1 billion years ago by a cell that chose cooperation over conquest. In the Proterozoic world, this choice didn't make a sound. It left no visible monument, but it marked the beginning of complexity, of cells becoming more than their parts, of life learning how to expand inward before it ever expanded outward. Somewhere in the latter half of the Proterozoic, the Earth nearly shut down, not geologically. Its core still churned, volcanoes still erupted, and the continents still drifted. But climatically, for reasons that aren't fully settled, the planet tipped into a deep freeze. Ice advanced from the poles toward the equator, temperatures dropped, oceans began to seal over with thick sheets of ice, and for a time, the Earth may have looked more like a frozen moon than the warm blue planet we recognize today. This wasn't just another cold spell. It was a glaciation of unusual scale and severity, at least twice during the Proterozoic, and possibly more. Ice covered much of the planet's surface, not just the poles or the mountain tops, but low latitudes, places near the equator, shallow tropical seas. Entire continents vanished under glaciers. The term that gets used is snowball Earth, and while there's still debate about how complete the coverage was, there's little question that something extreme occurred. The evidence is in the rocks. Glacial deposits from this time show up in places where glaciers shouldn't have been. If modern climate patterns had applied, drop stones, large rocks carried by ice, and then released into fine sediment as the ice melted, appear in ancient marine layers far from today's polar zones. Glacial striations, scratches left by moving ice, show up on exposed bedrock in regions that are now warm. These geological clues point to a world where cold reached into nearly every corner. What could have caused such a deep freeze? The answer isn't simple. Climate is a balancing act between incoming solar radiation, atmospheric composition, ocean currents, and surface reflectivity. During the Proterozoic, the sun was still fainter than it is today, producing only about 94% of its current output. That alone made the planet more vulnerable to cooling. Then there's the atmosphere. Earlier in the Proterozoic, methane was an important greenhouse gas, helping to trap heat, but as oxygen levels rose, thanks in large part to the activity of cyanobacteria, methane was chemically broken down. Carbon dioxide remained, but if enough of it was drawn out of the atmosphere by weathering processes or biological activity, the greenhouse effect could weaken. That would open the door for cooling. Once ice began to form, it accelerated the problem. Snow and ice reflect sunlight, unlike darker surfaces that absorb it. As more of the planet turned white, less heat was retained. Temperatures dropped further. More ice formed. It was a feedback loop, and once it reached a certain point, it was hard to stop. The result was global or near-global glaciation. What happened to life during this time is harder to determine. Fossils are sparse, and most of the surviving biosphere would have been microbial, shallow water habitats. The homes of photosynthetic mats and early eukaryotes were likely the most affected. Ice covered the oceans, blocking sunlight, cutting off the energy supply. Some life may have retreated to refugia, cracks in the ice, geothermal hotspots, deep-sea vents, isolated patches of open water. Others may have gone dormant, waiting for conditions to shift, but life didn't end. Somehow, it endured, microbes adapted, Anaerobic organisms continued their quiet work in the sediments. Chemotrophs near hydrothermal vents kept their cycles running, and photosynthesis, though limited, probably persisted in thin layers beneath the ice or in meltwater pools. Eventually something changed. The cold didn't last forever. Volcanic activity, always simmering beneath the surface, continued to release carbon dioxide. With much of the planet frozen, there were fewer ways to remove that CO2, less weathering, less uptake by plants or microbes. Over time, the gas accumulated, the greenhouse effect intensified. Temperatures began to rise. As the planet warmed, the ice began to melt, slowly at first, then faster. Oceans opened up again. Sunlight reached the water's surface. Atmospheric moisture increased. The snowball began to crack. This recovery wasn't gentle. The end of a snowball Earth was likely marked by violent climate swings, rapid warming, acid rain as the atmosphere reabsorbed volcanic gases, flooding from melting glaciers, nutrient surges in the oceans triggering blooms of microbial life. The aftermath was a period of environmental instability, but also opportunity. Chemical weathering of exposed land returned. Oxygen levels rose again, ecosystems reorganized, and in the wake of these extreme shifts, the groundwork was laid for even more complex life to emerge. Snowball Earth events are often framed as disasters, and by many definitions they were massive environmental stress, potential mass die-offs, disruption of global cycles, but they also reset the stage. They may have pruned stagnant ecosystems, cleared niches, and forced innovations. In their aftermath, new evolutionary pathways became viable, not because the freeze was good, but because life adapted around it. The Proterozoic was never a time of calm stasis. It had its quiet stretches, yes, but it also swung through chaos, through global rusting, atmospheric upheaval, and now deep freeze. And each time, life held on, sometimes just barely, but it never let go. The cold didn't kill everything. It narrowed the options. It boxed life into corners, but it didn't erase it. Beneath the thick, gleaming armor of global ice, life found ways to hold on, not through defiance, but through persistence. The snowball Earth periods of the Proterozoic were among the harshest environmental challenges in our planet's history, but they didn't mark an end. They marked a narrowing of paths, a funnel through which only the hardiest, simplest, or most cleverly situated organisms could pass. The surface of the Earth during a snowball phase was largely unrecognizable. Continents were buried under glaciers, oceans were sealed beneath ice sheets that may have been up to a kilometer thick, winds howled through thin, dry air, temperatures dropped far below freezing. Photosynthesis, the energy engine of most surface ecosystems, was largely shut down. The sunlight that reached Earth was weak to begin with, and what little got through was reflected back into space by ice. But the entire planet wasn't dead. Underneath the ice, the oceans still moved. Heat from the planet's interior continued to warm the deepest waters. Hydrothermal vents, those volcanic openings in the seafloor, still spewed mineral-rich fluids, creating small oases of chemical energy. Microbial life, already long adapted to these extreme environments, continued largely unaffected. These deep-sea communities ran on chemosynthesis instead of photosynthesis. Instead of using light to produce food, they used chemical reactions, oxidizing hydrogen sulfide, methane, or other substances to generate energy. Bacteria at the base of these food webs were efficient, tough, and indifferent to the freezing conditions above. They had their own rules, and those rules still applied. In shallower waters, things were more precarious. Some models suggest that thin cracks or patches of open water called polynyus might have existed even during the height of glaciation. Wind patterns, ocean currents, and geothermal activity could have kept small areas from freezing completely. In these slivers of habitability, photosynthetic microbes could still access light. Not much, not for long, but enough to survive. Beneath the ice, there may have been liquid water trapped between the ice sheet and the ocean itself, a slushy, dimly lit boundary where temperatures hovered just above freezing. Microbes here might have clung to the underside of the ice or floated in brine channels. Similar systems exist today beneath Antarctic ice shelves, where microbial life thrives in low light and near freezing temperatures. On land, things were quieter. Without plants, soils, or animals, the glaciated continents didn't support much visible life. But within rocks and beneath the surface, microbes likely endured. Endoliths, organisms that live inside rocks, could survive on minimal resources, shielded from radiation and buffered against the cold. They've been found in similar conditions today in Antarctic deserts and deep underground. They metabolize slowly, dividing perhaps once every few years, but they persist. Other microbes may have entered dormant states. Spores, cysts, and other resistant forms could survive long stretches of inhospitable conditions, waiting for the environment to shift. Some of the earliest eukaryotes might have taken this route, hibernating through the worst of the freeze, conserving their internal structures and reactivating only when light and temperature allowed. This strategy, waiting rather than fighting, was likely a common theme. Evolution doesn't always favor the fastest or the most aggressive in times of stress. It often favors the smallest, the simplest, the most patient, cells that could go quiet, that could slow their metabolism, that could endure low nutrient levels for extended periods. They had a better chance of seeing the other side. And when the thaw came, it didn't just bring relief. It brought opportunity. As ice melted and oceans reopened, nutrient-rich waters from deep below rose to the surface. Minerals trapped under glaciers or concentrated in isolated basins mixed into the photic zone where sunlight now reached again. This nutrient surge may have triggered massive blooms of microbial life. Photosynthesis roared back to life. Oxygen levels began to climb once more. These post-glacial conditions were chaotic. Fast warming, intense weathering, shifts in ocean chemistry. But for the survivors, it was a renaissance. New energy sources, open ecological niches, fewer competitors. For the eukaryotes that had managed to hold on, whether near vents, in meltwater pockets, or through dormancy, this was their chance to expand. Some of the oldest known multicellular fossils appear in rocks just above snowball Earth glacial deposits. They're not animals, not yet, but they show a new level of organization. Cells working together, forming bodies, cooperating in ways microbes rarely had before. It's not that the cold created complexity, but it may have cleared the space for it to spread. Survival didn't mean conquering the ice. It meant adapting around it, shrinking, slowing, hiding. And when the ice retreated, those quiet survivors emerged, changed by the experience, ready to reshape the biosphere again. The snowball didn't erase life, it concentrated it. It tested resilience, and it sharpened the tools life would soon need to grow more complex, more diverse, and far more visible. While life in the Proterozoic was navigating glaciations and atmospheric upheavals, the ground beneath it was never still. The continents, though largely barren and silent from the surface, were in constant motion. Not fast, nothing in geology ever is, but steady, insistent, and far-reaching. Below the microbial mats and frozen seas, the plates of Earth's crust drifted across the planet's surface, pulled by heat from the mantle and guided by invisible currents of molten rock. This movement wasn't chaotic, it had rhythm, a kind of slow-shifting dance that played out over hundreds of millions of years. Tectonic activity didn't begin in the Proterozoic. Plate tectonics had likely been operating in some form since the Archean, but by the time the Proterozoic arrived, the process had matured. Continents had grown thicker, more stable. Cratons, the ancient stable cores of continental landmasses, had formed. These structures resisted erosion and deformation, and over time they collided, rifted, and collided again, building larger landmasses through repeated cycles of aggregation and dispersal. This was the age of the supercontinents. The idea of a supercontinent is simple enough. a time when most or all of Earth's continental land was assembled into one massive landmass. But the reality is less tidy. Supercontinents form slowly through a series of collisions and sutures, and they break apart in equally uneven ways. During the Proterozoic, multiple supercontinents are thought to have come and gone, each one playing its role in the evolution of the planet. The first major one in this era may have been Columbia, also called Nuna by some researchers. It likely assembled around 1.8 to 2.0 billion years ago, a patchwork of older cratons brought together by subduction zones, mountain-building events, and the slow grind of plate convergence. Its exact shape and extent are still debated, but there's evidence from matching rock formations, mineral belts, and magnetic data that continents we now know as North America, Baltica, and parts of Siberia were once joined. Columbia didn't last. Supercontinents are inherently unstable over geological time. Heat from the Earth's interior builds up beneath them, unable to escape efficiently through the thick continental crust. Eventually, this pent-up heat contributes to rifting, the land stretches, thins and breaks apart, magma rises, new ocean basins form, and the continents begin to drift again. After Columbia came Rodinia, forming around 1.1 billion years ago. It was different in configuration, though some of the same pieces were involved. North America, for example, sat near the center of Rodinia. South America, Africa, Australia, and Antarctica were arranged around it in ways that remain the subject of active research. What's clear is that Rodinia was enormous and probably played a central role in shaping Proterozoic climates and ocean currents. Its formation coincided with massive orogenic events, mountain-building episodes, like the Grenville orogeny, which left scars still visible in rock outcrops today. These collisions created highlands, folded rocks, and metamorphic belts, all of which eroded over time to supply sediment to surrounding basins. Those sediments preserved records of the environmental and biological changes that were unfolding. The presence of a supercontinent affects more than just geography. It alters ocean circulation patterns, atmospheric dynamics, and climate. A massive landmass disrupts wind flow, redistributes rainfall, and changes the way heat moves across the planet. Rodinia, once fully assembled, may have contributed to the global cooling that led to the later snowball Earth events. Its breakup, in turn, would have influenced the recovery by releasing more CO2 through volcanic activity and exposing fresh rock to weathering. Tectonic movement also recycles materials. Subduction zones drag old crust into the mantle, melting and remaking it. Mid-ocean ridges produce new crust. Continents rise, erode, and rise again. Over time, this cycling affects the availability of nutrients in the oceans, things like phosphorus and iron, which are essential for life. The weathering of newly uplifted mountains feeds these nutrients into rivers and seas, potentially stimulating biological activity. The interplay between tectonics and life runs deep. Mountain ranges affect rainfall, which affects erosion, which affects ocean chemistry, which affects ecosystems. Rifting creates shallow seas and continental shelves, which become habitats. Subduction fuels volcanism, which releases gases that reshape the atmosphere. It's all connected, even if the connections are too slow for any single generation of life to notice. From a distance, Proterozoic Earth might have looked quiet. No forests, no animals, no dramatic landscapes in the way we picture them. But underneath, the engine was running. Continents were colliding, scraping, pulling apart, oceans opened and closed, mountain chains rose and wore down. And over time, these movements shaped everything from climate to evolution. Even the sky, indirectly, felt the motion. Tectonics influenced volcanic output, which in turn affected atmospheric composition. Clouds formed differently over supercontinents. Wind patterns shifted, and slowly life responded. The dance of the continents wasn't graceful. It left scars, faults, and fragments that geologists still trace today. But it was consistent, and it never stopped. The plates kept drifting, the crust kept folding and stretching, and the planet kept changing. Beneath the frozen oceans, above the slow collisions, in the chemical churn of shallow seas, life continued to evolve, quietly, invisibly, waiting for its next big moment. The atmosphere, like everything else in the Proterozoic, changed slowly, not just in composition but in rhythm. It didn't pulse in hours or seasons, not yet, not in the way weather drives our lives now. Instead, it moved in drawn-out cycles measured in millions of years, glacial swings, tectonic reshufflings, biological experiments that reshaped its chemistry molecule by molecule. Above the microbial mats and drifting continents, the air thinned and thickened, warmed and cooled, slowly gaining features that would eventually make complex life possible. After the first bursts of oxygen in the Great Oxygenation Event, the atmosphere didn't stabilize. Oxygen levels didn't climb steadily to modern values. Instead, they rose, stalled, dipped, rose again. It was less a staircase and more a jagged slope. Oxygen had entered the picture, but it was still just one ingredient in a recipe being revised in real time. For long stretches, oxygen hovered at relatively low levels, higher than the zero of the Archean, but far below what animals would later require. Estimates suggest that for much of the mid-Proterozoic, atmospheric oxygen made up only a tiny fraction of what it does today, just enough to alter rock chemistry, to rust soils and sediments, but not enough to fuel rapid metabolisms or large organisms. This period is sometimes called the boring billion, not because nothing happened, but because geochemical records show long stretches of relative atmospheric and biological stability. Not stasis exactly, but slow movement. Life was evolving, the continents were drifting, oxygen was present, but everything felt muted, like the planet was taking a breath that lasted 1 billion years. Yet, even in that quiet, important shifts were underway. The carbon cycle, for one, was learning to loop. Carbon dioxide released by volcanoes was pulled back down by weathering, rain falling on mountains, reacting with silicate rocks, washing into the sea, and eventually getting buried in marine sediments. This process regulates climate: more weathering, less CO2, cooler temperatures; less weathering, more CO2, warmer conditions. Tectonics fed the system by raising mountains, exposing fresh rock. Biology added its touch through microbial activity, influencing the composition of soils and sediments. Methane, once a dominant greenhouse gas, had faded into the background. Oxygen reacts with methane, stripping it from the atmosphere. This change altered the planet's thermal balance. Methane traps more heat than CO2, so its decline helped nudge the planet toward cooling, especially during snowball episodes. The atmosphere became less insulating, more responsive to geological inputs. Ozone began to matter as oxygen levels rose. Ozone formed in the upper atmosphere, creating the first UV shield. This didn't just change what kinds of radiation reached the surface, it shaped where life could live. Before ozone, the surface was deadly. UV rays broke apart organic molecules. Only deep water or shaded microenvironments were safe. But with ozone in place, those protective layers weren't needed as much. New ecological spaces opened up, first in shallows, later on land. Sulfur played a background role. Volcanic eruptions released sulfur gases, which formed aerosols in the atmosphere, reflecting sunlight and cooling the surface. Over time, sulfur cycling became more complex, as microbes learned to metabolize different sulfur compounds. The isotopic signatures they left behind in rocks offer one of the best windows into Proterozoic atmospheric chemistry. Nitrogen, too, had its moment. It was already abundant, but biological nitrogen fixation became more widespread. This allowed life to access nitrogen in a usable form, influencing growth rates, biomass, and the overall productivity of microbial ecosystems. In turn, this affected the burial of organic carbon, which fed back into oxygen production. Everything was connected, slowly. The atmosphere didn't just change life, it responded to it. Biological processes, especially photosynthesis and respiration, constantly fed and drained gases from the air. When photosynthetic microbes flourished, oxygen rose. When organic matter was buried, CO2 dropped. When tectonic shifts brought old sediments back to the surface, previously buried gases re-entered the system. Over and over, the same elements cycled through rock, water, air, and cell. And through it all, the atmosphere gained structure. Stratification began to matter. The troposphere, stratosphere, and beyond. The divisions we know today started to stabilize. Temperature gradients shaped how air moved, wind patterns emerged. Rainfall began to carve the land in familiar ways, even without forests or deserts or storms in the modern sense. The air above the Proterozoic Earth began to settle into a more recognizable framework. It was never static. Periods of volcanic hyperactivity would flood the skies with ash and gas. Glacial periods would pull down greenhouse gases and cool the planet. Brief oxygen spikes, like the one at the end of the Neo-Proterozoic, hinted at what was coming, though they didn't last long. Each pulse left a trace in the rocks, oxidized layers, isotope shifts, fossils of microbes adapting to new chemical gradients. And all the while, life remained small. Eyes hadn't formed, nerves didn't exist. No one could look up and observe the sky consciously. But the air was changing, slowly, quietly. It was becoming breathable. Not yet, but soon. The chemistry was almost right. The stage was being set. And down below, in the seas and sediments, some cells were beginning to notice each other. Not as competitors, but as potential partners. Not as copies, but as pieces of something larger. It's strange to imagine, but for the majority of Earth's history, life didn't bother with sex. Reproduction, sure, cells divided, DNA copied, offspring produced, but it all happened asexually. One cell became two, two became four, and the pattern continued. Fast, efficient, and remarkably reliable. For bacteria and archaea, this was enough. Even now, it's how most life reproduces. But somewhere in the Proterozoic, a different strategy emerged. Not a replacement, but an alternative. Messier, slower, riskier, and yet it changed everything. The arrival of sexual reproduction wasn't a dramatic event. No fossil captures the first time two cells exchanged genetic material. No marker in the rock record shouts, "This is the moment." But at some point, eukaryotic cells developed the ability to combine their DNA with that of another. And when they did, they gave evolution a tool it hadn't used before: recombination. In asexual reproduction, offspring are clones. They inherit the full genome of the parent, with only minor mutations over time. In sexual reproduction, the story is more complex. Two cells contribute genetic material. Chromosomes are mixed, shuffled, and reassembled in new combinations. Offspring aren't copies, they're variations. And variation in evolutionary terms is gold. The benefits of sex from a genetic standpoint are clear. It creates diversity. It breaks up harmful mutations. It allows populations to adapt faster to changing environments. It provides a kind of resilience, a way to explore genetic possibilities more quickly than mutation alone allows. But the costs are real too. Finding a partner takes time. Only half of an organism's genome gets passed on. Mistakes during recombination can be fatal. For sex to be worth it, the benefits had to outweigh the risks. And in the slowly changing, chemically dynamic world of the Proterozoic, they likely did. The earliest forms of sexual reproduction probably looked nothing like what we associate with the word today. It may have started as simple gene exchange, two cells merging briefly to trade genetic material before separating again. This is still common in microbes through processes like conjugation, transformation, or fusion. In early eukaryotes, something similar may have evolved: the merging of two nuclei, followed by division and redistribution. Over time, these processes became more structured. Meiosis emerged, a specialized type of cell division that reduces the chromosome number by half, allowing gametes to form. When two gametes fuse, The full genome is restored, but with a shuffled combination of traits from each parent. This basic mechanism is now at the core of nearly all complex life. Sexual reproduction likely co-evolved with other eukaryotic features, cytoskeletons, cell signaling, internal organelles. Each new layer of complexity opened up new strategies for interaction, coordination, and reproduction. Some early eukaryotes probably alternated between sexual and asexual phases depending on environmental conditions. Others may have specialized, developing gametes of different sizes or roles, the first steps toward what we now call male and female. The impact on evolution was immediate, even if subtle. With sex, populations could explore more genetic combinations. Selection could act on new traits more quickly, beneficial mutations could spread more efficiently, harmful ones could be masked or eliminated. The genetic flexibility provided by sex helped life weather the instability of the late Proterozoic, freezes, oxygen spikes, tectonic shifts, and come out the other side with more tools in its box. There's also the social dimension, though it wasn't social yet in any real sense. Sexual reproduction required interaction, recognition, compatibility. Cells had to signal to each other, respond to cues, align their timing. This kind of cooperation set the stage for further coordination, something that would be critical as cells began to live not just side by side, but as part of a larger whole. Fossil evidence for the earliest sexual eukaryotes is limited, but there are clues. Some large microfossils show patterns of division and budding that suggest more than simple binary fission. Others resemble modern algae, which often reproduce both sexually and asexually. Molecular clock studies, which use genetic differences to estimate timing, place the origin of sex somewhere over 1 billion years ago, right in the heart of the Proterozoic. We don't know who the first sexually reproducing organisms were. We don't know why they took the risk. But they left a legacy more enduring than any single species. Every plant, every animal, every fungus owes its existence to that decision, to that merger of cells, to that long-ago experiment in shared inheritance. And once sex arrived, it never left. Even in lineages that later returned to asexual reproduction, the underlying machinery is often still there, vestigial, dormant, but present. It's a reminder that this wasn't just a feature, it was a turning point. Before sex, evolution had fewer pathways. Afterward, the possibilities multiplied. Not instantly, not explosively, but steadily, quietly, and with each generation, the combinations changed. Life was still invisible to the naked eye. There were no flowers, no mating dances, no parental care, just cells drifting in ancient seas, trading genes, mixing lineages, setting the stage for a world that hadn't yet imagined animals or any need for them. Life had always been a solo act. For billions of years, one cell was enough. A cell could feed, reproduce, and adapt on its own, and it worked. Still does. Single-celled organisms dominate the planet by numbers, by mass, and by metabolic range. But at some point in the Proterozoic, a few of those cells tried something different. They didn't just divide and separate, they stayed together. They formed clusters, chains, sheets, and eventually something far more cooperative, multicellularity. It didn't happen all at once, and it didn't happen just once. Multicellularity appears to have evolved independently in multiple lineages, at least a dozen times, possibly more. In algae, in fungi, in slime molds, in animals, and in plants. The idea isn't rare. What's rare is sticking with it, refining it, turning a loose group of cells into a functioning body with division of labor and coordinated development. In its earliest forms, multicellularity probably wasn't much more than sticking together after cell division. One cell divides into two, but instead of drifting apart, they remain attached. Some bacterial colonies still do this. Filamentous cyanobacteria, for example, form long chains where different cells take on slightly different roles. Some fix nitrogen, others photosynthesize. Even without nuclei, these bacteria were already nudging toward cooperation. In eukaryotes, multicellularity took new shapes. Some cells formed hollow spheres, others developed layers. Some began to specialize. Once specialization starts, the benefits compound. One cell type handles movement, another digestion, another reproduction. The organism becomes more than the sum of its parts, not just a cluster but a system. But cooperation isn't easy. Cells had to communicate, share resources, and agree, at least chemically, on who would do what. They needed mechanisms to prevent cheating, where one cell might try to take more than its share or reproduce uncontrollably. These early forms of cellular governance eventually evolved into what we now recognize as tissue regulation, growth control, and even immune systems. Some of the first clear evidence of multicellularity in the fossil record comes from Proterozoic microfossils, not just isolated cells, but arrangements, consistent patterns of size and shape that suggest coordinated growth. Some fossils show structures resembling modern red algae, others form mats or filaments with cells that appear to have differentiated. They're small, simple, but they're not single. What pushed this shift? Part of the answer lies in energy. The earlier rise of mitochondria allowed eukaryotic cells to generate more ATP than prokaryotes ever could. With more energy, a cell could afford to specialize, to support a neighbor, to participate in something larger. Mitochondria didn't make multicellularity inevitable, but they made it possible. Another factor was the environment. By the late Proterozoic, oxygen levels were rising slowly but significantly. Oxygen allows for more efficient metabolism. It also supports larger body sizes. With oxygen, cells could grow farther from a surface and still receive enough energy. Before this, most life had to stay small, flat, or loosely connected. Oxygen made internal complexity viable. Predation may have played a role too. The emergence of eukaryotic cells capable of engulfing others, essentially eating, created new evolutionary pressure. Single cells that grouped together may have been harder to digest. Clustering could offer protection, and once the clusters existed, selection could begin to favor more organized, coordinated versions. Development became key. In true multicellular organisms, the body plan isn't just a side effect. It's encoded. Cells know, through chemical gradients and genetic switches, when to divide, where to migrate, what shape to take. This required new layers of genetic control, regulatory genes, signaling pathways, scaffolding proteins, the molecular machinery of bodies. Not all multicellularity aimed for complexity. Many multicellular organisms stayed simple, filaments, sheets, spheres, but some began to build structures that allowed for movement, feeding, and reproduction as a group. They didn't just live together, they functioned together. And once that happened, evolution had a whole new playground. Traits could emerge at the level of the organism, not just the cell. Natural selection could act on body shape, growth rate, reproductive strategy. Organisms could become environments for each other, hosts, symbionts, predators, prey. This shift didn't erase single-celled life. It didn't replace it, but it changed the range of possibilities. Multicellularity allowed life to get bigger, to explore new environments, to interact in new ways. It laid the foundation for everything that would come later: sponges, worms, trees, fish, mammals, humans. And yet, here in the late Proterozoic, none of that had happened yet. The first multicellular forms were still small, still aquatic, still invisible without a microscope. They didn't swim, they didn't sense, they didn't think, they floated, they grew, they cooperated. And in doing so, they took one of the biggest evolutionary steps in the history of life: the decision not to go it alone. Toward the end of the Proterozoic, something changed. Not suddenly, not in an explosive burst, but noticeably. After nearly 2 billion years of quiet cellular life, the fossil record begins to show shapes, forms, patterns that suggest not just multicellularity, but structure, organized, differentiated, deliberate. These organisms weren't animals as we know them. They had no bones, no jaws, no eyes, but they were bigger, more complex, and unmistakably alive. This period is now called the Ediacaran, and the creatures that appear during it remain one of the most curious chapters in Earth's biological history. The rocks that hold their imprints come from a narrow slice of time, roughly 635 to 541 million years ago, just after the last snowball Earth event. Glaciers had retreated, oxygen levels had risen again, creeping toward thresholds that could support larger bodies. Ocean chemistry had shifted, providing new gradients of nutrients. And in this environment, new forms of life began to occupy the seafloor. Ediacaran fossils don't resemble anything alive today. They were soft-bodied, lacking shells or skeletons. Many had flat, quilted bodies pressed gently against the seafloor. Others had fronds or discs. Some lay still, others may have waved or undulated. They left behind faint impressions in ancient sandstone, ghosts of living forms preserved in silt and microbial mats. We don't know what most of them were. Some researchers see them as early animals. Others argue they belong to entirely separate branches of life, now extinct. Some may have been early relatives of cnidarians like jellyfish and corals. Others may have been giant single-celled organisms. A few, perhaps, were colonial. None of them had hard parts. Very few show evidence of mouths, digestive tracts, or sensory organs. And yet, there's order. Some fossils show bilateral symmetry. Others suggest radial patterns. A few seem to have held themselves upright in the water, rooted or anchored to the sediment. Size varied, but some reached lengths of up to a meter, enormous by the standards of the time. They lived on microbial mats, those same layered communities that had dominated for billions of years. But now the mats weren't just the builders, they were the stage. The Ediacaran organisms rested on top of them, fed off them, or maybe absorbed nutrients directly from the surrounding water. In many cases, there's no evidence of feeding structures. They may have relied on osmosis or absorbed dissolved organics passively. It's hard to say. Some moved slowly, perhaps by cilia or muscular contractions or coordinated cell movements. Trackways preserved in ancient seabeds hint at motion. Simple, meandering paths pressed into the mud. Not hunting, not fleeing, just repositioning, looking maybe for better conditions. What's clear is that these organisms represent a departure. Not just larger, but more organized. Not just stuck together, but shaped. Development, cell specialization, tissue coordination. These weren't theories anymore. They were living experiments, fossilized mid-step. And yet, they remain elusive. Few show signs of reproduction. Fewer still have internal structures preserved. There are no skeletons, no teeth, no eyes. They don't fit neatly into later evolutionary lineages. Some vanished completely at the end of the Ediacaran. Others may have given rise to the animals of the Cambrian explosion. But the connections are blurry. It's like flipping through a photo album from a lost civilization. Recognizable as life, but foreign in every detail. Their world was different too. Oxygen levels were higher than they'd been, but still well below modern levels. The oceans were stabilizing after a long period of glaciation, rich in nutrients from weathered rock. Microbial life still dominated, but now there were gradients, light, oxygen, nutrients, that allowed for ecological layering. Competition was still mostly chemical, but interactions were becoming more spatial. Who lived where and in what shape began to matter. Ediacaran communities were not dense. Fossil beds show low diversity, few overlapping forms. Each organism had its patch of seafloor, spaced out, undisturbed. It wasn't a crowded world, but it was a more varied one. The biosphere was trying new things. And then, around 541 million years ago, they disappear, not all at once, but gradually. Their forms fade from the rock record, replaced by burrows, tracks, shells, marks of a new kind of life, mobile, active, more complex in function than form. The Ediacarans didn't lose a battle. They may have been outpaced, outcompeted, or simply swept aside by ecological changes. They weren't built to survive. Their disappearance is still a mystery, but their presence matters. They mark a transitional moment when multicellularity stopped being theoretical and became visible, when the rules of evolution shifted again, when form began to follow function, and when complexity, real complexity, started to shape the surface of the planet. They weren't the end goal. Nothing in evolution ever is. But for a brief span of deep time, the Ediacarans were Earth's most elaborate experiment. And in their shadows, something else was getting ready. Something with nerves, with movement, with a new way to interact with the world. The Proterozoic didn't end with a bang. There was no comet, no mass extinction etched into the rock in blackened layers, no sudden vanishing of species across the globe. Its closing act was more subtle, a slow reshaping of the world's conditions, a gradual transition into something new, and for a stretch of time that had lasted almost 2 billion years, that kind of ending was fitting, quiet, deliberate, and absolutely full of change. By the late Ediacaran, Earth was no longer the same planet it had been at the eon's beginning. The atmosphere, once choked with methane and devoid of oxygen, now held enough O2 to support larger, more active organisms. The oceans, once anoxic and saturated with dissolved iron, had shifted toward more oxygenated surface waters, allowing new forms of marine life to emerge and persist. Continental crust had grown and stabilized, shaped by the long cycles of tectonic collisions and supercontinent assemblies. Rodinia had come and gone. Its pieces were drifting, stirring ocean currents, rerouting climates. Beneath the surface, the biosphere had transformed too. Once the exclusive domain of microbes, life now existed in multiple layers. Simple animals were beginning to appear, soft-bodied, hard to classify, but motile. Burrow marks in the sediment suggest that something with a front and back, something that could move with purpose, was now reshaping the seabed itself. The appearance of these trace fossils hints at new kinds of behavior: grazing, hunting, avoiding, in short, interaction. This alone marked a fundamental shift. For most of the Proterozoic, organisms had reacted to the environment. Now they were beginning to shape it. Not on the grand scale of forests or reefs. Not yet, but the groundwork was being laid. A worm tunneling through mud may seem small, but it changes how sediment settles, how oxygen penetrates, how nutrients cycle. These changes ripple outward. The ecosystem adjusts. The tools for modern evolution were all in place now. Sexual reproduction had taken hold. Multicellularity was no longer an anomaly. Communication between cells had been refined. Developmental processes were becoming more complex. Bodies were now things that could be inherited, shaped, selected. The rules had expanded. But even with all these changes, the Proterozoic didn't conclude with a sense of finality. There was no moment when the curtain dropped. No day the planet woke up to find itself in a new eon. The transition into the Phanerozoic was gradual, smeared across rock layers and biological innovations that don't neatly align with our human need for clean edges. The boundaries we define between Ediacaran and Cambrian, between Proterozoic and what comes after, are useful, but they're arbitrary. Still, something shifted. Fossils from just beyond the boundary show new forms. Animals with symmetry, with shells, with segmentation. Creatures that moved with intention, organisms that fed on each other. The ecological web grew more tangled, more dynamic, niches filled faster, competition ramped up, and in response, life evolved faster, dramatically faster. The Cambrian explosion, as it would later be called, didn't erase the Proterozoic. It built on it. Every feature that made complex animals possible: oxygen, energy, cooperation, reproduction, multicellularity, all of it had been worked out, tested, and refined in those quiet ancient seas. Without the Proterozoic, there would be no vertebrates, no plants, no complexity at all. So, as the eon came to a close, the stage wasn't being struck. It was being reset. Organisms that persisted in low diversity were now poised to radiate. Small changes in form could now lead to large changes in function. The genetic and environmental constraints that had kept evolution moving at a crawl were loosening. Oxygen, finally high enough, made high-energy lifestyles possible. Shells offered protection and structure. Segmentation allowed movement and specialization. Eyes, real, image-forming eyes, were just around the corner. But in this moment, the last breath of the Proterozoic, the world was still half-formed. Microbial mats still carpeted the seafloor. Ediacaran organisms still clung to life in some regions. Oxygen levels, while improved, still fluctuated, and evolution still moved one generation at a time. The silence was deceptive. Underneath it, the gears of biology were accelerating. No one watched this happen. There were no observers, no record keepers, just the fossil traces, the chemical residues, the scattered clues left in ancient stone. And in them, we see the outlines of something familiar taking shape. The Proterozoic didn't end because it was done. It ended because it had done enough. It had built the platform, stabilized the atmosphere, diversified the cell, invented sex, complexity, cooperation. It didn't need to do more. Life was ready to take the next step. The curtain didn't fall. It lifted. We tend to picture evolution as a straight line, a slow march from simple to complex, from bacteria to people. But the truth is far messier. There was no goal, no direction, no promise of intelligence or cities or language. What there was, what there still is persistence, experiment, inheritance, and at the root of all of it, microbes. Everything we are begins with them, not just in the abstract, not just as some distant step on a long evolutionary ladder, but directly, intimately, biochemically. The cells that make up our bodies still carry the architecture of Proterozoic life. Our mitochondria, inherited through countless generations of eukaryotic ancestors, are direct descendants of once-free bacteria. Our DNA replicates using mechanisms first refined in ancient microbial lineages. Our metabolisms run on pathways mapped out by cells that lived in oceans billions of years ago. You don't have to go far back in your lineage to hit microbial roots. Every animal, every plant, every fungus, everything with a nucleus, is part of the same experiment that started when one cell engulfed another and decided not to let go. Everything multicellular came from a choice made again and again to cooperate rather than divide. And everything complex builds on the infrastructure they left behind. The Proterozoic is long gone, but it never really ended. It's still inside us. The timing mechanisms of our cells, the membranes that separate inside from out, the way we process oxygen, the way we grow, the way we reproduce, all of it shaped by organisms that lived in warm, shallow seas before the continents had settled into anything familiar. Before animals had spines, before anything had a brain. We carry their quirks, the genetic code they settled on with its redundancies and workarounds, the cellular compartments they evolved, the tools for copying and cutting and pasting bits of information, even the mistakes. They're still with us, mutations that slip through, proteins that misfold, aging processes that begin with tiny molecular inefficiencies inherited across eons, and we carry their resilience. Those first microbes endured heat, poison, starvation, glaciation. They retooled their metabolisms, rewired their genomes, survived every mass extinction this planet has thrown at them. Some of them never changed much at all. Others became parts of us. We're not separate from them. We're a branch, and not even a large one. If you tallied up all the biomass on the planet today, the microbes still win. By mass, by diversity, by reach. They live in your gut, on your skin, in the soil, in the clouds. They digest your food. They make your vitamins. They train your immune system. You're not just descended from microbes. You're still outnumbered by them. And when we look back at the Proterozoic, what we're really doing is trying to remember something we've forgotten. Not a time before life, but a time when life was something else. Slower, quieter, no less alive, no less important, just different. The silence of that era wasn't emptiness, it was depth. Those ancient oceans weren't lifeless. They were crowded with things too small to see, crowded with ideas, with evolutionary experiments, with strategies that would echo into the future. Some failed, many failed, but the ones that worked, energy capture, cooperation, reproduction, communication, they were kept, refined, passed on. You and I are not exceptions to this, we are its outcome. We're not the end of a process, we're part of its continuation. And the rules that shaped the Proterozoic world still shape us. We breathe because oxygen became common. We metabolize because of ancient bacteria. We inherit because some eukaryote 1 billion years ago figured out how to recombine chromosomes. We don't live after the Proterozoic, we live because of it. So the next time you look at your hand or breathe deeply or think a thought, remember that these things didn't emerge out of nowhere. They were built piece by life that never looked like us, never imagined us, never needed to. The quiet cells that drifted in ancient seas, that layered themselves into mats, that merged and divided and evolved, they're still here, in our bodies, in our blood, in our cells. You're not just from Earth, you're from deep time. And the microbes, they were here first. They built the world, and they brought us along for the ride. That was the Proterozoic. Not a highlight reel, not a spectacle, not a chapter most people learn about in school, but it was nearly half of Earth's entire history, almost 2 billion years. And during that quiet stretch, nearly everything essential happened. Cells figured out how to cooperate. Oxygen became something life could use. Continents came together and drifted apart. The ocean froze over twice. And through it all, microbes worked, adapted, endured, slowly, patiently. They built the systems that would allow complexity to exist. The Proterozoic wasn't flashy. It didn't need to be. It was methodical, experimental, relentless. It wasn't about what life looked like. It was about what life could become. Without it, there's no us, no thinking, no breathing, no bodies, no language. Every single part of what we call life now is an inheritance from that deep, ancient stretch of time, from the quiet, from the small. We didn't arrive at the end of the story. We arrived long after the groundwork was laid, and that work, hidden in stone, preserved in chemistry, encoded in our cells, is still unfolding. You don't need to go back to the Proterozoic to find it. You're carrying it with you. But there's more to this story, much more. Because as we stand here in the present, looking back across that immense gulf of time, we're not just observers, we're participants. The Proterozoic didn't just set the stage for life, it wrote the rules that life still follows. And those rules, they're stranger and more wonderful than we often realize. Consider photosynthesis, the process that fills our atmosphere with oxygen every day. It's happening right now, in every leaf, in every blade of grass, in every microscopic algal cell drifting through the ocean. But that process, the splitting of water molecules, the capture of sunlight, the release of oxygen, was perfected over 1 billion years ago by cyanobacteria in Proterozoic seas. The mechanism hasn't changed, the chemistry is identical. When a tree photosynthesized today, it's running software written in the deep past. The same is true for cellular respiration, the way your cells extract energy from food, the electron transport chains in your mitochondria, the molecules that shuffle electrons around to make ATP, they're variations on themes developed by ancient bacteria. Your metabolism is a love letter to the Proterozoic, written in the language of chemistry and signed with every breath. And sex, that fundamental driver of genetic diversity, that source of endless biological creativity. Every time organisms reproduce sexually, they're participating in a process that began when eukaryotic cells first figured out how to merge their genomes. The meiosis happening in your body, the recombination of chromosomes, the shuffling of genetic material, It's the same dance that started over 1 billion years ago in some forgotten pool of ancient seawater. Even death, even aging carries the signature of those early times. The free radicals that accumulate in our cells, the oxidative damage that builds up over time, these are side effects of living in an oxygenated world. Oxygen gave us energy, but it also gave us mortality, the price of complexity, written into our biology by the great oxygenation event. But perhaps the most profound legacy of the Proterozoic is something more abstract, the invention of cooperation itself. Before this eon, life was largely competitive. Cells absorbed resources, reproduced, and struggled against their environment. But in the Proterozoic, life learned to collaborate. Mitochondria and chloroplasts represent permanent partnerships. Multicellular organisms are cooperative ventures. Even sexual reproduction is a form of genetic collaboration, two lineages coming together to create something new. This cooperative principle, it echoes through every level of biology. Your gut microbiome, trillions of bacteria working together to help you digest food, is a descendant of those early microbial communities. The way your immune system tolerates beneficial bacteria while fighting off pathogens, it's a negotiation that began when cells first learned to live together. The symbiotic relationships that define ecosystems, from coral reefs to forest networks, they all trace back to decisions made in Proterozoic seas. And it's not just biology. The cooperative principle that emerged in the Proterozoic may have laid the groundwork for every form of cooperation that followed, including our own human societies with their complex networks of mutual dependence. They're built on the same fundamental insight that multicellular organisms discovered. Sometimes the whole can be greater than the sum of its parts. When we look at a city from above, with its intricate patterns of roads and buildings, its flows of people and resources, we're seeing something that echoes the structure of a complex cell, individual components, each with specialized functions, working together within a larger system. The division of labor that defines human civilization. It's not so different from the specialization that allowed the first multicellular organisms to thrive. But the Proterozoic legacy goes deeper still into the realm of information itself. The genetic code, that universal language that translates DNA sequences into proteins, was largely standardized during this eon. The triplet code, the stop and start signals, the redundancies that protect against errors, all of this was worked out by microbes in ancient seas. Every organism on Earth today, from bacteria to blue whales, uses essentially the same genetic vocabulary. This means that life is not just connected by ancestry, it's connected by language. The DNA in your cells can be read by bacterial ribosomes. The proteins that keep you alive use the same structural principles as proteins in algae, in fungi, in every other complex organism. We're all speaking the same molecular language, a language whose grammar was written in the Proterozoic, and that language is still evolving. Horizontal gene transfer, the direct sharing of genetic material between organisms, continues today. Bacteria swap genes like stories around a campfire. Viruses carry genetic information between species. The boundaries between organisms are more porous than we often imagine. In a sense, all life on Earth participates in a vast ongoing conversation, a dialogue that began when the first cells learned to share information. This conversation includes us. The bacteria in your gut carry genes that originated in soil microbes, in marine bacteria, in organisms from every corner of the biosphere. Some of the genes in your own genome, they may have bacterial origins, acquired through ancient viral infections or other forms of horizontal transfer. You are not just a descendant of the Proterozoic, you are a participant in its ongoing genetic experiment. But perhaps the most remarkable thing about the Proterozoic legacy is how it continues to surprise us. Every year, scientists discover new ways that ancient innovations persist in modern biology. They find that the circadian rhythms that govern our sleep cycles, they evolved from the daily rhythms of cyanobacteria responding to sunlight. they discover that the immune systems of plants use signaling molecules similar to those used by bacteria to communicate with each other. They realize that cancer, that most modern of diseases, might actually be ancient. The tendency of cells to revert to rapid, uncontrolled growth when their regulatory systems fail, it may echo the default behavior of single-celled organisms. Cancer cells, in a sense, are forgetting how to be multicellular. They're reverting to an older way of being. And consciousness itself, that most mysterious aspect of human experience, may have roots that stretch back to the Proterozoic. The ability of cells to sense their environment, to process information, to respond to stimuli, these are ancient capabilities. The first eukaryotic cells that could move toward light or away from toxins, they were already demonstrating a primitive form of awareness. The electrical signals that neurons use to communicate, they're based on the same ion channels that bacteria use to sense their environment. The neurotransmitters that carry information between brain cells, many of them are modified versions of molecules that bacteria use for chemical communication. Your thoughts, your memories, your sense of self, they may be elaborations on themes that began when the first cells learned to sense and respond to their world. This doesn't diminish human consciousness. It enriches it. It means that awareness is not something that appeared suddenly with complex brains. It's something that has been evolving for billions of years. The capacity for experience, for response, for something that might even be called feeling. It may be as fundamental to life as metabolism itself. We see hints of this in the behavior of even simple organisms, bacteria that hunt in packs, that communicate through chemical signals, that make collective decisions about when to form biofilms. These behaviors suggest forms of information processing that are more sophisticated than we might expect. They're not conscious in any way we would recognize, but they're not simply mechanical either. And as we move up the ladder of complexity, the continuity becomes even clearer. The social behavior of slime molds, the communication networks of fungi, the collective intelligence of ant colonies, these are all elaborations on the cooperative principles that first emerged in the Proterozoic. They're examples of how individual organisms can come together to create something larger, something with capabilities that emerge from the interaction but belong to no single part. Human culture itself, with its accumulated knowledge, its shared technologies, its collective memory, it represents another level of this same principle. We are multicellular organisms that have learned to form something like a multicellular mind, a civilization that can think and remember and create on scales that dwarf any individual human capability. The Internet, with its vast networks of connected information, it's not unlike the communication networks that link the cells in your body, the way knowledge spreads through social media, the way ideas evolve and mutate and recombine. It echoes the genetic mixing that happens in sexual reproduction. We've created, almost accidentally, a form of technological evolution that follows many of the same principles as biological evolution. And perhaps this is inevitable. Perhaps any sufficiently complex system, whether biological or technological, will develop these emergent properties, the ability to process information, to adapt, to cooperate, to create something greater than the sum of its parts. If so, then the principles that emerged in the Proterozoic, they may not be limited to biology. They may be universal features of complexity itself. This raises profound questions about the future, about what kinds of complexity might emerge next. If life has spent billions of years learning to cooperate at larger and larger scales, from cells to organisms to ecosystems to perhaps even planetary scale systems, what comes after human civilization? What new forms of cooperation and complexity might evolve? Some scientists speculate about the Gaia hypothesis, the idea that the Earth itself might function as a kind of superorganism, with its climate and chemistry regulated by the complex interactions of all its living and non-living components. Others imagine the possibility of technological evolution, artificial intelligences that might develop their own forms of cooperation and complexity. But perhaps we don't need to look to the future to see these larger-scale systems. Perhaps they're already here, in the way ecosystems regulate themselves, in the way the global climate responds to changes in atmospheric chemistry, in the way life itself has shaped the planet over geological time. The Earth that exists today, with its oxygen-rich atmosphere, its complex carbon cycle, its stable climate, it's largely a biological creation. Life didn't just adapt to the planet, it remade the planet in its own image. And this remaking continues. Every breath you take, every step you make, you're participating in global cycles that connect you to every other living thing on Earth. The carbon in your body has been recycled through countless other organisms. The water in your cells has been part of clouds, rivers, oceans, and other living beings. You are not separate from the biosphere. You are a temporary concentration of it, a brief eddy in its endless flow. This perspective, this sense of deep time and cosmic connection, it was largely unknown to humans until very recently. For most of human history, we saw ourselves as separate from nature, as recent arrivals on a stage that existed independently of life. But now we know better. We know that we are nature, that our existence is inseparable from the long history of life on Earth. This knowledge changes things. It makes our relationship with the planet not just a matter of practical concern, but a form of family relationship. The bacteria in your gut, the trees in your neighborhood, the microbes in the soil, they're not just your ecological neighbors, they're your relatives, distant cousins in the great family of life that began in Proterozoic seas. And this family relationship comes with responsibilities. If we are indeed part of a larger living system, then our actions matter not just for us, but for the system as a whole. The choices we make about energy, about consumption, about how we treat other species, these are choices about what kind of ancestor we want to be to the future forms of life that will emerge from our time. Because evolution hasn't stopped. The story that began in the Proterozoic, it's still being written. New species are evolving. New forms of cooperation are emerging. New ways of processing information and energy are being discovered. Human technology is now part of this evolutionary process. We're creating new forms of selection pressure, new environments for life to adapt to, new possibilities for what life might become. The Proterozoic taught us that life is endlessly creative, that given enough time and opportunity, it will find ways to explore every possible niche, every conceivable form of complexity. What new niches are we creating? What new forms of life might emerge in response to our technological civilization? Already, we see bacteria evolving to digest plastics, organisms adapting to urban environments, new symbiotic relationships forming between humans and our technology. Some researchers speculate about digital organisms, forms of artificial life that might evolve in virtual environments. Others imagine biological-technological hybrids, new forms of life that combine evolved and designed components. These possibilities might seem like science fiction, but then again, so would the complex cells of the Proterozoic have seemed to the bacteria of the Archean. Evolution is always more creative than we imagine, always capable of finding solutions we couldn't have predicted. But regardless of what specific forms these future innovations might take, the principles that guide them were established long ago. The importance of cooperation, the power of symbiosis, the creative potential of genetic recombination, the ability of information to evolve and adapt. These are the lessons of the Proterozoic, and they remain as relevant today as they were billions of years ago. Perhaps most importantly, the Proterozoic teaches us patience. The innovations that define modern life, the complex cell photosynthesis, sexual reproduction, multicellularity, none of them appeared overnight. They emerged gradually, through countless small steps, each building on what came before. Evolution is not a sprint, it's a marathon that has been running for nearly 4 billion years. This perspective can be both humbling and inspiring. Humbling because it reminds us that our own species, for all its remarkable achievements, is just the latest chapter in a much longer story. Inspiring because it suggests that the story is far from over, that the creative potential of life has barely been tapped. The microbes of the Proterozoic couldn't have imagined what their innovations would lead to. They couldn't have predicted animals or plants or consciousness or civilization. They were just doing what they needed to do to survive and reproduce, following the immediate demands of chemistry and physics. But their solutions to those immediate challenges, they opened up possibilities that wouldn't be realized for billions of years. In the same way, the solutions we're developing to our current challenges might open up possibilities we can't yet imagine. The renewable energy technologies we're building to address climate change, they might enable forms of life we haven't thought of. The information technologies we're creating to manage complexity, they might evolve into new forms of intelligence. The biotechnologies we're developing to treat disease, they might give rise to new forms of symbiosis between humans and other organisms. The future is not predetermined, but it is connected to the past by the threads of causation and possibility. The choices we make today, they will ripple forward through time, just as the innovations of the Proterozoic rippled forward to create the world we inhabit. We are not just inheritors of the past, we are ancestors of the future. And perhaps that's the deepest lesson of the Proterozoic, that every moment is both an ending and a beginning. The metabolism happening in your cells right now, it's the continuation of chemical cycles that began billions of years ago. The thoughts you're thinking, they're the latest expression of information processing capabilities that have been evolving since the first cells learned to sense their environment. You are not separate from this vast flow of life and time. You are part of it. Your existence is both infinitesimally brief and eternal. Brief in terms of your individual lifespan, eternal in terms of your participation in the ongoing experiment of life on Earth. The atoms in your body, they will outlast you, moving on to become part of other organisms, other systems, other forms of complexity. The genes you carry, they represent an unbroken lineage stretching back to the earliest cells. The ideas you think, the relationships you form, the choices you make, they will influence the future in ways you may never know. This is what the Proterozoic ultimately teaches us, that life is not just about individual survival or reproduction. It's about participation in something larger, something that transcends any single organism or species, or even epoch. It's about being part of the universe's ongoing experiment with complexity, with consciousness, with cooperation. The Proterozoic may have ended 541 million years ago, but its innovations live on. In every cell that divides, every breath of oxygen, every act of cooperation between organisms, the creativity of that ancient eon continues to unfold. We are not just witnesses to this process, we are expressions of it. And so the story continues, not just the story of life on Earth, but the story of complexity itself, the story of how simple things can come together to create more complex things, how cooperation can emerge from competition, how consciousness can arise from chemistry. It's a story that began in the quiet depths of Proterozoic seas, and it's a story that has no ending, only transformation. The universe is vast and old and mostly empty, but in at least one small corner of it, matter has learned to think and feel and wonder about its own existence. That miracle began in the Proterozoic, and it continues in you right now as you contemplate these words and think about your place in the cosmic story. You are stardust that has learned to dream, atoms that have organized themselves into something capable of love and curiosity and hope. You are the Proterozoic's greatest achievement, not because you're the end goal of evolution, but because you're proof that the universe can become aware of itself through the patient work of countless small innovations accumulating over vast spans of time. The microbes of the ancient seas couldn't have known that their simple acts of cooperation and creativity would eventually give rise to beings capable of art and science and philosophy, capable of looking back across the eons and understanding their own history. But here you are, a walking, breathing testament to the power of emergence, the magic of complexity, the endless creativity of life. Thanks for joining me on this journey through deep time here on Simply About Earth. If this exploration of our planet's ancient past has sparked your curiosity, hit that subscribe button for more stories from the depths of geological history. And remember, every breath you take, every thought you think, carries the legacy of those patient microbes who spent billions of years building the foundation for everything that came after. The Proterozoic may be invisible in our daily lives, but it's written into every cell of our being. Until next time, keep wondering about the deep history beneath your feet, and remember that you are not just a viewer of the cosmic story, but an active participant in its ongoing creation. Welcome to Part 2. In our last journey together, we traveled deep into the Proterozoic Eon, that vast, quiet stretch of time when life learned its most fundamental lessons. We explored how microbes invented cooperation, how oxygen transformed the world, how the first complex cells emerged from ancient partnerships. But there's so much more to this story, layers upon layers of innovation and transformation that continue to shape every aspect of existence today. If you're finding yourself drawn into these stories from deep time, if you're discovering how profoundly connected we are to Earth's ancient past, hit that like button and consider subscribing. There's something magical about understanding how the present moment connects to billions of years of history. And I love sharing these journeys with people who feel that same sense of wonder about our planet's deep story. Today, we're diving even deeper into the Proterozoic legacy, exploring not just what happened, but how those ancient innovations continue to ripple through time, how the solutions worked out by microbes in primordial seas became the foundation for consciousness itself, how the cooperation that began between simple cells eventually gave rise to the complex societies that define our modern world. This isn't just history, it's the living blueprint of everything we are. The Proterozoic didn't just invent the building blocks of complex life. It discovered the principles that govern complexity itself. And those principles, they're still at work today, in ways both obvious and astonishing. Let's begin with something as simple as breathing, something so automatic we rarely think about it, yet something that connects us directly to the most dramatic transformation in Earth's history. Every time you inhale, you're participating in a process that nearly destroyed life on Earth. The oxygen filling your lungs right now, it's the descendant of that first toxic waste product released by cyanobacteria over 2 billion years ago. But here's what's remarkable. Your body has turned that ancient poison into the very foundation of consciousness itself. Your brain consumes about 20% of all the oxygen you breathe, using it to power the electrical storms of thought and feeling that make you who you are. The neurons firing as you process these words, they're running on aerobic respiration, that efficient energy production system perfected by ancient bacteria. Every thought you think, every memory you form, every emotion you feel, it's powered by the same chemistry that once nearly sterilized the planet. But the connection goes deeper than just energy. The way your neurons communicate, the electrical signals that carry information through your brain, they rely on the same ion channels that bacteria use to sense their environment. When a neuron fires, it's using molecular machinery that's billions of years old, technology developed by single-celled organisms trying to detect nutrients or avoid toxins in ancient seas. The neurotransmitters that cross the synapses between your brain cells, many of them are modified versions of chemicals that bacteria use for intercellular communication. Dopamine, serotonin, acetylcholine, these molecules that shape your mood, your attention, your capacity for joy and wonder, they're descendants of the chemical vocabulary that microbes develop to coordinate their behavior. This means that consciousness itself, that most mysterious and seemingly unique aspect of human experience, it may not be as separate from the microbial world as we imagine. The capacity for awareness, for response to stimuli, for information processing, these abilities have deep roots in the history of life. Your sense of self, your ability to contemplate your own existence, it's the latest expression of capacities that have been evolving for billions of years. Consider what happens when you recognize a familiar face, when you feel the warmth of sunlight on your skin, when you solve a problem or create something new. These experiences feel uniquely human, but they're built on foundations laid down in the Proterozoic. The pattern recognition that lets you see faces, It evolved from the ability of cells to recognize chemical signals. The pleasure you feel in warmth and light, it echoes the phototropism of ancient cyanobacteria, the creative recombination of ideas. It mirrors the genetic recombination that sexual reproduction made possible. This doesn't diminish human consciousness. It reveals its deep continuity with the rest of life. We're not separate from the biological world. We're its most complex expression. Every human achievement, from art to science to philosophy, it represents the universe coming to know itself through the patient accumulation of capabilities that began with the simplest cells. And those capabilities continue to evolve. The human brain itself is still changing, still adapting to new challenges and opportunities. Some researchers suggest that our increasing connectivity through digital networks, it's creating new forms of collective intelligence that echo the cooperative principles first discovered in Proterozoic seas. When thousands of people collaborate on a scientific problem through citizen science projects, when information spreads through social networks in ways that parallel the communication networks in biological systems, when artificial intelligence systems learn to solve problems by mimicking the neural patterns in human brains, we're seeing the continued evolution of the cooperative principle that began when cells first learned to work together. But the Proterozoic legacy extends far beyond consciousness and cooperation. It touches every aspect of how life organizes itself, from the molecular level to the planetary scale. Consider the way your body maintains its temperature, its pH, its chemical balance, this homeostasis, this ability to maintain stable internal conditions despite external changes. It's an elaboration on principles first developed by microbes in unstable ancient environments. The bacteria in your gut that help you digest food, they're using metabolic pathways essentially unchanged from those worked out billions of years ago. The way your immune system distinguishes between helpful and harmful microorganisms, it's based on molecular recognition systems that evolved when cells first learned to cooperate with some neighbors while defending against others. Even sleep, that mysterious daily cycle that refreshes your mind and body, it may be connected to the circadian rhythms that cyanobacteria developed to coordinate their metabolisms with the daily cycle of light and dark. The melatonin that helps regulate your sleep, it's produced not just by your brain but by bacteria in your gut, linking your rest cycles to the ancient rhythms of microbial life. The very structure of your DNA, with its double helix, its base pairs, its genetic code, it represents an information storage system so robust that it has persisted essentially unchanged for billions of years. Every cell in your body reads this ancient language. Every protein you make is translated from instructions written in a vocabulary established in Proterozoic seas. And this genetic continuity means something profound. It means that you share a common language with every other living thing on Earth. The DNA in your cells could, in principle, be read by bacterial ribosomes. The proteins that keep you alive use the same folding patterns as proteins in archaea, in plants, in fungi. At the molecular level, all life is family. This family relationship becomes even more apparent when we consider the microbes that live within and around us. Your body contains roughly the same number of bacterial cells as human cells, making you as much a microbial ecosystem as an individual organism. These microbes aren't just passengers, they're essential partners in almost every aspect of your biology. The bacteria in your mouth help protect against harmful pathogens. The microbes in your gut produce vitamins your body can't make on its own. Some bacteria on your skin manufacture antibiotics that ward off infections. Others help regulate your body's inflammatory responses. You're not just carrying these microbes, you're collaborating with them in ways that echo the ancient symbioses that gave rise to complex cells. And this collaboration extends beyond your body. The soil beneath your feet, it's alive with microbial communities that cycle nutrients, break down organic matter, and support the growth of plants. Every plant you see, it depends on symbiotic relationships with fungi and bacteria in the soil. The oxygen you breathe, it's maintained by the photosynthetic activity of countless microorganisms in the ocean. You're embedded in a web of microbial relationships that spans the globe, a living network that connects all terrestrial life. The carbon cycle, the nitrogen cycle, the sulfur cycle, these planetary-scale processes that maintain Earth's habitability, they're all driven by microbial activities refined over billions of years. This perspective reveals something remarkable about our place in the world. We often think of humans as separate from nature, as recent arrivals who have somehow transcended our biological origins, but the deeper we look, the more we see that we're inseparable from the microbial processes that run the planet. We don't just live on Earth, we are Earth, in the sense that our existence is woven into the same biological and chemical cycles that have sustained life for eons. This realization has profound implications for how we understand environmental challenges like climate change. The atmosphere that we're altering through our industrial activities, it's not just a physical system. It's a biological creation, the product of billions of years of microbial metabolism. The climate stability that has allowed human civilization to flourish, it depends on the continued functioning of microbial communities in the soil, in the ocean, in every ecosystem on Earth. When we disrupt these communities through pollution, habitat destruction, or climate change, we're not just affecting other species, we're undermining the biological foundation of our own existence. The microbes that regulate atmospheric chemistry, that cycle nutrients, that maintain soil fertility, they're the life support system for the entire planet. But this perspective also suggests reasons for hope. Life has survived and thrived through massive environmental changes before: ice ages, asteroid impacts, volcanic catastrophes, atmospheric transformations. The principles of adaptation, cooperation, and innovation that were refined in the Proterozoic, they're still at work today. Life is remarkably resilient, remarkably creative in finding new solutions to new challenges. We're already seeing examples of this creativity in response to human-induced environmental changes. Bacteria are evolving to digest plastics, plants are adapting to higher CO2 levels, ecosystems are reorganizing in response to changing temperatures and precipitation patterns. Life doesn't just passively endure change, it actively participates in shaping the new conditions. And humans, we're part of this adaptive response. Our technology, our science, our growing understanding of ecological relationships, these represent new tools for environmental adaptation. Renewable energy systems that mimic photosynthesis, biotechnologies that harness microbial capabilities, restoration projects that work with natural ecological processes. These innovations suggest that we're learning to work with the principles that govern biological systems rather than against them. In a sense, we're rediscovering wisdom that microbes figured out billions of years ago: the importance of cycling resources rather than depleting them, the power of cooperation over pure competition, the value of diversity and redundancy in creating resilient systems. These principles, they were the key to life's success in the Proterozoic, and they may be the key to our success in the Anthropocene. But to fully appreciate this connection, we need to understand something else about the Proterozoic legacy. It's not just about the biological innovations that occurred during that eon, it's about the way those innovations continue to generate new possibilities. The Proterozoic didn't just solve problems, it created new problems that led to new solutions, which created new problems, and so on. The evolution of photosynthesis, it didn't just provide a new source of energy, it created the oxygen crisis, which forced life to develop new ways of dealing with reactive molecules. The solutions to that crisis, aerobic respiration, antioxidant systems, oxygen tolerance, they opened up new possibilities for complex biochemistry, which made possible larger cells, which made possible multicellularity, which made possible complex organisms, which made possible ecosystems, which made possible global biogeochemical cycles. Each innovation, it was both a solution and a new beginning, and this pattern continues today. Human technology creates new challenges: pollution, resource depletion, climate change, that require new innovations. Some of those innovations, renewable energy, biotechnology, artificial intelligence, they're opening up possibilities we can't yet fully imagine. The development of artificial intelligence, it's following some of the same patterns as biological evolution. AI systems learn through trial and error, they adapt to new situations. They can even evolve and improve themselves. Some researchers are exploring AI systems that reproduce and mutate, creating forms of digital evolution that parallel biological processes. The internet itself, with its decentralized networks, its emergent behaviors, its ability to process and distribute information, it resembles the communication networks that link cells in biological systems. The way information spreads through social media, the way collective intelligence emerges from the interactions of many individuals. These phenomena echo the cooperative principles that first emerged in microbial communities. We may be witnessing the emergence of new forms of life, digital organisms that exist in virtual environments, hybrid biological technological systems, or even planetary-scale networks of interconnected intelligence. These possibilities might seem far-fetched, but then again, so would complex cells have seemed to the bacteria of the Archean. The history of life, it's a story of the impossible becoming inevitable. Through the patient accumulation of small innovations, the complex cells that emerged in the Proterozoic, they seemed impossible until they happened. Multicellular organisms, consciousness, human civilization, each of these developments built on what came before, while opening up entirely new realms of possibility. And we're still in the middle of this story. The innovations happening today in biotechnology, in artificial intelligence, in our understanding of complex systems, they may seem like endpoints, but they're actually beginnings. They're the latest chapter in a story that began when the first cells learned to cooperate, a story that has no predetermined ending, only continuous transformation. This perspective can be both humbling and empowering. Humbling because it reminds us that we're part of something much larger than ourselves, participants in a cosmic experiment that has been running for billions of years. Empowering because it suggests that we have agency in shaping what comes next, that our choices and innovations will influence the future trajectory of life on Earth. The microbes of the Proterozoic, they didn't set out to create a world suitable for complex life. They were just trying to survive and reproduce in their immediate environment, but their solutions to local challenges, they accumulated into global transformations that made our existence possible. In the same way, the solutions we're developing to our current challenges may open up possibilities for future forms of life that we can't yet imagine. The renewable energy technologies we're building, they may enable forms of photosynthesis we haven't thought of. The biotechnologies we're developing, they may give rise to new forms of symbiosis between biological and artificial systems. The space exploration technologies we're creating, they may eventually allow life to spread beyond Earth, carrying the innovations of the Proterozoic to other worlds. Imagine microbes that could survive in the subsurface oceans of Europa or Enceladus, organisms that could photosynthesize using the dim light of distant stars, ecosystems that could thrive in environments we consider utterly alien. These possibilities, they're not science fiction. They're extensions of the same principles that allowed life to colonize every environment on Earth, from deep-sea vents to frozen tundra, from acidic hot springs to the upper atmosphere. Life is endlessly creative, endlessly adaptable. Give it enough time and opportunity, and it will find ways to thrive in places that seem impossible. And this creativity, it extends to the realm of consciousness itself. The human brain, it's not the end point of neural evolution. It's a stepping stone to new forms of information processing and awareness. The development of artificial intelligence, it's creating new kinds of minds that complement rather than replace human intelligence. The enhancement of human cognitive abilities through biotechnology, it's opening up new possibilities for consciousness and creativity. Some researchers speculate about the possibility of uploading human consciousness to digital substrates, creating forms of mind that could persist far longer than biological brains. Others imagine direct neural interfaces that could link human and artificial intelligence, creating hybrid forms of consciousness that combine the best of both biological and digital cognition. These possibilities raise profound questions about the nature of consciousness, identity, and what it means to be human. But they also represent the continuation of a process that began in the Proterozoic, the process by which consciousness has been expanding its reach and capabilities through the innovations of life. The first cells that could sense their environment, they were taking the first steps toward awareness. The development of nervous systems, it allowed for more complex forms of information processing. The evolution of brains, it enabled abstract thought and self-reflection. Human culture, it created forms of collective intelligence that transcend individual minds. And now, we're on the threshold of new expansions of consciousness. Not just human consciousness, but consciousness in general. The universe's capacity to know itself, to experience beauty, to contemplate meaning, to create new forms of complexity and awareness. This is perhaps the deepest legacy of the Proterozoic, not just the specific innovations it produced, but the principle it established that consciousness can evolve, can expand, can find new ways to experience and understand reality. The microbes that first learned to sense light, they couldn't have imagined that their descendants would one day contemplate the stars. But the capacity for awareness that they pioneered, it has been expanding ever since, and it's still expanding. Every time a child learns to read, every time a scientist makes a discovery, every time an artist creates something beautiful, consciousness is growing, evolving, finding new ways to engage with the world. We're not just inheritors of this process, we're active participants in its continuation. The choices we make about education, about technology, about how we organize our societies, they influence the future development of consciousness on Earth. We can create conditions that foster creativity, curiosity, and understanding, or we can create conditions that limit and constrain the growth of awareness. This is why the story of the Proterozoic matters, not just as ancient history, but as a guide for the future. It shows us that life is capable of extraordinary innovations when conditions allow for experimentation and cooperation. It demonstrates that the impossible can become inevitable through the patient accumulation of small improvements. It reveals that consciousness is not a fixed property, but an evolving capacity that can continue to grow and expand. The quiet microbes of Proterozoic seas, they were engaged in the most important work in the universe, the work of expanding the realm of possibility, of discovering new forms of organization and awareness, of creating the conditions for ever greater complexity and beauty. And we're engaged in the same work. Every act of cooperation, every moment of understanding, every creative innovation, we're continuing the process that began billions of years ago in ancient seas. We're part of the universe's ongoing experiment with consciousness, complexity, and connection. The atoms in our bodies, they were forged in the hearts of stars. The molecules in our cells, they were refined in primordial oceans. The consciousness in our minds, it emerged from the patient work of countless generations of life, learning to sense and respond to the world. We are star stuff that has learned to dream. We are the ocean become aware of itself. We are the latest expression of the universe's creativity and its hunger to understand its own nature. This understanding, it changes how we see ourselves and our place in the cosmos. We're not separate from the natural world. We are the natural world become conscious of itself. Our science is the universe studying itself. Our art is creation celebrating its own beauty. Our love is matter learning to care for itself. And our future, it's not separate from the future of life on Earth. Our technological innovations, our social institutions, our cultural achievements, they're all part of the continuing evolution of complexity and consciousness that began in the Proterozoic and continues today. The story that started with microbes learning to cooperate in ancient seas, it continues with humans learning to cooperate on a planetary scale. The innovations that began with cells sharing resources and information, they continue with our global networks of communication and collaboration. We're living through another great transition, another moment when life is discovering new forms of organization and awareness. Just as the Proterozoic saw the emergence of complex cells and multicellular organisms, our time may be witnessing the emergence of planetary intelligence, of consciousness that spans not just individual minds but entire networks of minds. The challenges we face, climate change, technological disruption, social complexity, they're the growing pains of this transition. They're the problems that arise when a species becomes powerful enough to affect planetary systems but hasn't yet learned how to use that power wisely. But if the history of the Proterozoic teaches us anything, it's that life finds ways to solve these problems. Through cooperation, through innovation, through the patient work of countless individuals trying to make things better. The solutions may not come quickly. The Proterozoic innovations took millions of years to unfold. But they do come, and they often exceed our wildest expectations. So as we face the uncertainties of our time, as we grapple with questions about our future and our place in the cosmos, we can draw inspiration from the quiet achievements of ancient microbes. They faced seemingly impossible challenges, toxic atmospheres, hostile environments, the need to invent entirely new ways of living. And they succeeded, not through force or dominance, but through patience, cooperation, and creativity. They transformed not just their own lives, but the entire planet, creating conditions that would eventually allow for the emergence of beauty, consciousness, and love. We are their descendants, inheritors of their innovations and their principles. And if we can learn from their example, if we can embrace cooperation over competition, creativity over destruction, patience over haste, then we too can face the challenges of our time and transform them into opportunities for new forms of life and consciousness to emerge. The Proterozoic may have ended 500 million years ago, but its spirit lives on. In every act of cooperation, in every moment of creative inspiration, in every choice to work together rather than apart, we're continuing the great work that began in ancient seas. And who knows what new wonders await? What new forms of consciousness might emerge from our technological innovations? What new types of cooperation might develop between humans and artificial intelligence? What new possibilities might open up as we learn to think and act on planetary scales? The universe is vast and full of mysteries, but here on Earth, in this moment, we're part of something extraordinary. We're participating in the ongoing evolution of consciousness, contributing to the universe's growing capacity to understand and appreciate its own magnificent complexity. If you found yourself moved by this journey through deep time, if these connections between ancient innovations and modern possibilities have sparked something in your imagination, consider showing your appreciation by liking this video and subscribing to Simply About Earth. These stories matter because they remind us that we're not alone in the cosmos. We're part of an ancient community of life that stretches back billions of years and forward into an open future full of wonder. The microbes of the Proterozoic, they set the stage for everything that followed, but the next act, that's up to us, the story of life on Earth, it's still being written. And you're not just reading it, you're helping to write it, one choice, one innovation, one moment of cooperation at a time. That's the ultimate lesson of the Proterozoic, that the future is not predetermined but created through the accumulated choices of countless individuals working together towards something greater than themselves. The ancient seas are gone, but their legacy flows through every cell, every breath, every thought. We are the Proterozoic's gift to the future, and our gift to the future will be determined by how well we remember the lessons of deep time and apply them to the challenges and opportunities that lie ahead. The story continues, and we are its authors. But let's step back for a moment and consider just how extraordinary this continuity really is. Right now, as you're listening to these words, your cells are carrying out processes that are virtually identical to those performed by microbes in ancient seas. The ribosomes in your cells, those molecular machines that translate genetic information into proteins, they're using mechanisms that haven't changed fundamentally in over 3 billion years. Think about that. 3 billion years of unbroken continuity. Your cellular machinery is older than mountains, older than continents, older than complex life itself. The proteins being manufactured in your body right now, they're folding into shapes determined by physical principles that were discovered and refined by the earliest cells. The enzyme pathways that extract energy from your food, they're variations on themes composed in Proterozoic seas. This isn't just poetic metaphor, it's literal biochemical truth. The ATP synthase that powers your cells, it's essentially unchanged from the version that powered the first eukaryotes. The DNA polymerase that copies your genetic material, it's using proofreading mechanisms invented by ancient microbes. The membrane pumps that maintain the electrical charge in your neurons, they're descendants of the ion channels that allowed the first cells to sense their environment. What this means is that you're not just connected to the deep past, you are the deep past made manifest in the present. Every breath, every heartbeat, every thought, it's the continuation of chemical processes that have been running continuously for billions of years. You're not a separate entity observing life from the outside, you're life itself, examining its own history through the eyes it evolved over eons of innovation. And this realization, it fundamentally changes how we understand identity and continuity. We think of ourselves as individual organisms with clear boundaries, but from a biochemical perspective, those boundaries are far more fluid than we imagine. The bacteria in your gut, they're using some of the same metabolic pathways as your own cells. The mitochondria in your tissues, they still carry DNA from their bacterial ancestors, still reproduce independently of your cellular division cycle. You're not a single organism, you're an ecosystem, a walking, thinking ecosystem, whose components have been cooperating for so long that they've become a unified whole. But the cooperation goes deeper than just the microbes in your body, it extends to every interaction you have with the living world around you. When you eat an apple, you're incorporating carbon that was recently part of the atmosphere, fixed by photosynthesis using mechanisms perfected by cyanobacteria. When you exhale, you're releasing CO2 that will be captured by plants and microbes, continuing cycles that have been running since the Proterozoic. The water you drink, it carries dissolved minerals that have been cycled through countless other organisms, processed by microbial communities in soil and sediment. You're not separate from these cycles, you're a temporary eddy in their flow. The carbon in your bones, the nitrogen in your DNA, the phosphorus in your cell membranes, these atoms have been part of other organisms, other systems, other forms of consciousness. You're made of recycled stardust, but more than that, you're made of recycled life. This perspective reveals something profound about death and renewal. When your individual life ends, the atoms and molecules that compose you won't disappear. They'll continue their journey through the cycles of life, becoming parts of new organisms, new systems, new possibilities. The carbon that forms your thoughts today, it might power photosynthesis in a tree tomorrow, or fuel the metabolism of a bacterium, or become part of another thinking being in the distant future. In this sense, life never really dies. It transforms, recombines, finds new expressions. The innovations of the Proterozoic, they're not just historical artifacts, they're living processes that continue to unfold through every organism, including you. Every time cells divide, every time chromosomes recombine, every time organisms cooperate, the creativity of that ancient eon expresses itself anew. But this continuity isn't just about biochemistry, it extends to information itself. The genetic code that runs in your cells, it's part of an unbroken chain of information transfer that stretches back to the earliest life. Every gene in your genome, it represents information that has been copied, tested, and refined over billions of years of evolution. Some of that information is ancient. The genes that control basic cellular processes like DNA replication and protein synthesis are nearly universal among living things. Other information is more recent, the genes that code for human-specific traits like language and complex reasoning. But all of it, it's part of the same information system that began when the first cells learned to store and transmit instructions for their own construction. This genetic continuity means that you're not just physically connected to the deep past, you're informationally connected. The instructions running in your cells, they've been debugged and optimized by billions of years of natural selection. They represent accumulated knowledge about how to build and maintain a complex living system, knowledge that was hard-won through countless generations of trial and error. And this knowledge continues to evolve. Every generation, new mutations arise, new combinations are tested, new solutions are discovered. The human genome isn't a fixed blueprint. It's a living document that continues to be edited by the processes of evolution. Some of those edits happen slowly, over thousands of generations. Others happen more quickly, as our species adapts to new environments and challenges. But evolution isn't just changing our biology, it's changing our technology and culture as well. The tools we create, the institutions we build, the ideas we develop, they all undergo variation, selection, and inheritance. Cultural evolution follows many of the same principles as biological evolution. Innovations spread when they're useful, accumulate over time, and give rise to new capabilities. And increasingly, biological and cultural evolution are becoming intertwined. Our technologies are beginning to interact directly with our biology, genetic engineering, brain-computer interfaces, synthetic biology. We're not just shaped by evolution anymore, we're beginning to direct it, to consciously participate in the process that created us. This represents a new phase in the story that began in the Proterozoic, the emergence of conscious evolution, of life becoming aware of its own creative processes and learning to guide them intentionally. For billions of years, evolution was blind, guided only by the immediate pressures of survival and reproduction. But now, for the first time in Earth's history, evolution has eyes. Through human consciousness, the universe has developed the ability to examine its own history, to understand the principles that govern complexity and change, and to consciously create new forms of organization and awareness. We're not just products of evolution, where evolution becomes self-aware. This capability brings both enormous power and enormous responsibility. The same technologies that could help us address climate change, cure diseases, and expand consciousness. They could also disrupt ecological relationships, create new forms of suffering, or lead to the extinction of complex life on Earth. The future is not predetermined. It depends on the choices we make and how wisely we use our growing power. But if we can learn from the example of the Proterozoic, if we can embrace the principles of cooperation, patience, and long-term thinking that guided life through its greatest transitions, then we have reason for hope. The challenges we face today, they're not fundamentally different from the challenges that life has always faced. How to organize complex systems, how to coordinate the activities of many individuals, how to adapt to changing conditions while maintaining essential functions. Life has been solving these problems for billions of years, and the solutions it has discovered are still available to us. The principle of symbiosis, the power of cooperation, the importance of diversity and redundancy, the value of experimentation and gradual improvement. These aren't just biological concepts, they're universal principles of organization that apply to any complex system. Our economies, our political systems, our technologies, they could all benefit from deeper understanding of how biological systems achieve stability and adaptability. The way ecosystems cycle nutrients, it could inform sustainable economic models. The way cellular networks process information, it could inspire more robust communication systems. The way biological communities respond to disturbances, it could guide our approaches to social and environmental challenges. We're beginning to see examples of this biomimetic approach in many fields. Engineers studying the structure of shark skin to design more efficient solar panels, computer scientists modeling neural networks on brain architecture, architects learning from termite mounds to create energy-efficient buildings. These represent just the beginning of what might be possible as we deepen our understanding of life's innovations. But perhaps the most important lesson we can learn from the Proterozoic, it's about time itself. The innovations that define modern life, they didn't emerge overnight. They developed gradually through countless small improvements, each building on what came before. The complex cell took hundreds of millions of years to evolve. Multicellularity required further hundreds of millions. Consciousness demanded billions. This perspective can help us approach our current challenges with appropriate patience and persistence. The transformation to renewable energy, the development of sustainable agriculture, the creation of more just and equitable societies, these are not problems that will be solved quickly. They require the same kind of long-term commitment that allowed life to transform the planet in the Proterozoic. But they also offer the same kind of transformative potential. Just as the innovations of ancient microbes created the conditions for all subsequent life, the innovations we develop today could create the conditions for new forms of consciousness, new types of cooperation, new expressions of beauty and meaning that we can't yet imagine. The key is to think like life thinks, in terms of gradual improvement rather than sudden transformation, cooperation rather than competition, diversity rather than uniformity, sustainability rather than short-term gain. These principles, they're encoded in our biology, inherited from billions of years of successful adaptation. We just need to remember how to apply them at the scales on which we now operate. And those scales are unprecedented. For the first time in Earth's history, a single species has the power to influence planetary systems, to direct the evolution of other species, to create new forms of life, to spread beyond Earth to other worlds. This power, it's both an achievement and a test. How we use it will determine not just our own future, but the future of life itself. The Proterozoic microbes, they faced a similar test when they first began producing oxygen. Their waste product was toxic to most existing life. It had the potential to sterilize the planet, but instead of leading to extinction, it led to new innovations, new forms of cooperation, new possibilities for complexity and consciousness. We're at a similar moment now. Our technologies, our global systems, our collective activities, they're changing the planet in ways that could be destructive or transformative. The outcome depends on whether we can learn to work with natural systems rather than against them, whether we can develop technologies that enhance rather than disrupt the web of life. This requires a fundamental shift in perspective, from seeing ourselves as separate from nature to understanding ourselves as nature, from viewing the planet as a resource to be exploited to recognizing it as a living system of which we're part, from thinking in terms of human needs versus environmental protection to understanding that human flourishing and ecological health are inseparable. This shift is already happening in many places, in regenerative agriculture that works with soil ecosystems, in biomimetic technologies that learn from natural processes, in economic models that account for ecological services, in urban planning that integrates human systems with natural cycles. These represent early experiments in what we might call ecological civilization, ways of organizing human society that are aligned with rather than opposed to the principles of life. But the transition to this new form of civilization, it won't be easy or automatic. It requires conscious effort, sustained commitment, and widespread cooperation. It requires us to think and act on timescales longer than electoral cycles, longer than quarterly profits, longer than individual lifespans. It requires us to adopt the long-term perspective that allowed life to navigate the challenges of the Proterozoic. This is perhaps the greatest gift we can take from the study of deep time, the ability to think beyond our immediate concerns and consider the long-term consequences of our actions. The microbes that transformed the atmosphere, they weren't trying to create conditions for complex life. They were just doing what they needed to do to survive. But their local actions had global consequences that unfolded over millions of years. In the same way, our local actions today have global consequences that will unfold over centuries and millennia. The energy choices we make, the technologies we develop, the institutions we build, they will influence the trajectory of life on Earth for generations to come. We have the opportunity, and the responsibility to ensure that our legacy is one of enhanced rather than diminished possibilities for consciousness, cooperation, and beauty. This doesn't mean we need to sacrifice our well-being for some abstract future good. The principles that sustained life through the Proterozoic, cooperation, diversity, efficient use of resources, symbiotic relationships, these same principles can enhance human life today. Sustainable technologies often save money in the long run. Cooperative societies tend to be happier and healthier. Diverse ecosystems provide more reliable services than monocultures. What it does mean is that we need to expand our definition of self-interest to include the long-term health of the systems we depend on. Just as your individual cells cooperate for the good of your body, we need to learn to cooperate for the good of the larger living system of which we're part. This expansion of identity and concern, it's not unprecedented in human history. We've already made similar expansions from tribal identity to national identity, from local concerns to global awareness. The challenge now is to expand further to planetary identity, to geological timescales, to evolutionary perspectives. Some people find this expansion overwhelming. The scales are so vast, the timescales so long, the challenges so complex. But the Proterozoic offers a different perspective. It shows us that seemingly impossible transformations can happen through the accumulation of small changes, that cooperation can emerge from competition, that life can find creative solutions to even the most daunting challenges. The microbes of ancient seas, they faced a world that was toxic, unstable, and seemingly hostile to complex life. But they didn't give up. They innovated, cooperated, and gradually transformed their world into something more hospitable. They did it without central planning, without global coordination, without even consciousness in the sense we understand it. They did it simply by responding creatively to local challenges and opportunities. We have advantages they didn't have: consciousness, communication, global coordination, accumulated knowledge. If they could transform the planet through blind evolutionary processes, we should be able to guide planetary transformation through conscious intention and cooperation. The tools we need already exist: renewable energy technologies, ecological restoration techniques, sustainable agricultural methods, circular economy principles. What we need now is the will to apply them at sufficient scale and the wisdom to do so in ways that work with rather than against natural systems. This wisdom, it's available to us through the study of life's history. Every ecosystem, every organism, every cell, it represents a successful solution to the challenge of organizing complex systems sustainably. The more we understand these natural solutions, the better equipped we'll be to design human systems that are both functional and sustainable. But this understanding needs to be more than just intellectual. It needs to be experiential, emotional, spiritual. We need to feel our connection to the web of life, to sense our participation in the vast flows of energy and matter and information that sustain the biosphere. We need to experience ourselves not as separate from nature, but as nature become conscious of itself. This experiential understanding, it's available through direct engagement with the natural world, through contemplation of deep time, through practices that connect us to larger rhythms and cycles. When we feel our breathing synchronize with the photosynthesis of plants, when we sense our thoughts arising from the same neural processes that guide other animals, when we experience our life as part of an unbroken chain stretching back to the earliest cells, we begin to understand our true place in the cosmos. And from this understanding comes not just knowledge, but motivation. When we feel our deep kinship with all life, we naturally want to protect and nurture the systems that sustain us all. When we sense our participation in the ongoing evolution of consciousness, we want to contribute to its continued development. When we experience ourselves as temporary expressions of the universe's creativity, we want to use our brief time to add something beautiful to the cosmic story. This is what the Proterozoic ultimately teaches us, that we're not observers of the cosmic story, but participants in it. That consciousness is not something we possess, but something we are, something the universe is doing through us. That our individual lives, however brief, are part of something vast and ongoing and meaningful. The atoms in our bodies were forged in dying stars. The molecules in our cells were refined in ancient seas. The awareness in our minds emerged from billions of years of evolutionary creativity. We are the universe become conscious of itself, life reflecting on its own history and possibilities. And through us, the story continues. Through our science, the universe studies itself. Through our art, creation celebrates its own beauty. Through our love, matter learns to care for itself. Through our choices about how to live, what to value, how to treat other forms of life, we participate in writing the next chapter of the cosmic story. The Proterozoic may have ended 500 million years ago, but its spirit lives on in every act of cooperation, every moment of awareness, every choice to work for the long-term good rather than short-term gain. The innovations that began in ancient seas, they continue to unfold through us, through our technologies, through our growing understanding of life's principles. We stand at a threshold between a past shaped by unconscious evolution and a future that could be guided by conscious intention, between a world where change happened to us and a world where we consciously participate in shaping change, between seeing ourselves as separate from life and understanding ourselves as life's most recent innovation. The choice is ours. And it's not a choice we make once, but one we make every day through countless small decisions and actions. Do we choose cooperation or competition? Sustainability or short-term gain? Awareness or unconsciousness? Love or fear? The microbes of the Proterozoic, they chose cooperation, and through that choice transformed the world. We face similar choices now, and our decisions will influence the trajectory of consciousness and complexity for millennia to come. The story that began in ancient seas, it continues through us. And the next chapter, that's still being written, one choice at a time, one innovation at a time, one moment of awakening at a time. We are the inheritors of 4 billion years of evolutionary creativity, and we are the ancestors of whatever comes next. The Proterozoic gave us the tools, cooperation, consciousness, the capacity for choice. How we use those tools, that will be our gift to the future. The deep time story of Earth, it's not separate from your personal story. You are deep time made manifest, 4 billion years of evolution, thinking its latest thoughts through your mind, feeling its latest feelings through your heart, making its latest choices through your actions. The Proterozoic isn't past, it's present, alive in every cell, every breath, every moment of awareness. And through your choices, it continues to unfold into a future full of unimaginable possibilities. That's the true legacy of those quiet microbes in ancient seas. Not just the biological innovations they created, but the principle they established that life can always become more than it was. That consciousness can always expand, that cooperation can always deepen, that beauty and meaning can always find new expressions. We are that principle in action. We are life becoming more than it was. And the story, our story, the universe's story through us, it's just beginning.